Every 2 years, Tiger teams are competed to tackle important and timely questions at hand. And the current set of Tiger teams are listed on the left part of this slide here, which include applications like developing data products to be used in environmental justice data portals, and to quantifying health impacts of small agricultural fires. HACAST is just one immediate avenue where I encourage you all to get involved with the health and air quality program. It's kind of a shorter term way to get in the know of what's happening. All the meetings are public. The next one is scheduled to be in April with the exact dates to be announced soon. It'll be in St. Louis as well as virtually. And I encourage interested parties to visit haycast.org to learn more and sign up for their newsletter to find out more about what's going on. We also value our connection with stakeholders during air quality, in the air quality community during airborne field campaigns. Last year, I co-organized the Tracer AQ mission in collaboration with the Texas Commission on Environmental Quality to assist with enhancing air quality planning by using state-of-the-art observations from aircraft and ground-based perspectives to better understand pollution emissions, the role of overwater ozone, and the preparation of the transition to geostationary air quality measurements from TEMPO, particularly in Houston, Texas. So if you go to the next slide, and speaking about TEMPO and looking ahead, our next big thing going on is that TEMPO is launching in just a few months, which is NASA's first geostationary air quality monitoring satellite. It stands for tropospheric emissions, monitoring of pollution, and it'll be able to measure column densities of nitrogen dioxide, ozone, and formaldehyde with the capability of resolving aerosol optical depth and aerosol layer height and other aerosol properties every hour of the day during the daytime. So to accelerate science after launch, I'm co-organizing the Synergistic TEMPO Air Quality Science Study, or STACS, which will include airborne proxies for TEMPO, as well as additional airborne and ground-based measurements in 3 major cities in Los Angeles, Chicago, and New York. And NASA isn't alone in this effort either, as this summer includes many other federal and local field efforts in summer 2023 in all these domains, all focused on improving our understanding of domestic air pollution. So finally, our portfolio is also growing with respect to fire activities, which is important due to the growth of wildfires in the Western US as consequence to climate change. And in one study, which is highlighted at the top here and highlighted in the New York Times in September, suggested that these fires are actually resulting in setbacks and successes of the Clean Air Act. So within the health and air quality portfolio, looking ahead, there are a few new things going on in the future. One is a project led by June Wang from the University of Iowa, who is partnering with air quality agencies to improve confidence in decisions made in relation to the transport of wildfire smoke. And then we'll also have continued work on the impact of smaller agricultural burns on human health, which are harder to detect with satellite data. And also the science, aeronautics, and space technology mission directorates are all collaborating together on an effort called FireSense, which aims to improve the understanding of these trends in wildfires due to climate change. So if you go to the last slide, which is just has my contact information and a few links, and I'll just wrap up by reiterating that I'm looking forward to seeing the presentations today. I will be in and out during the meeting, but I'm happy to answer questions as I will be here most of the time. And if I don't have the answer for it, I will find the answer or the right person to talk to. So I appreciate your attention, and thanks.
Wonderful. Thank you, Helena. And thank you, Laura. Sorry. I was going to say that Helena Chapman is also putting some links, some very important links in our chat that everyone can check out. But really appreciate that presentation. And we'll take questions right after in our Q&A section. So Woody, I found you here on this list, so I should be able to provide you with grand control of this presentation.
Take control. Great. Okay.
Okay.
Perfect. Thank you very much. Thanks, Laura, for getting us going with sort of atmospheric focused application for health and air quality. I'm going to take a step back here and talk about the applied sciences program more generally, how it fits within earth science. how we operate and how you can get involved with it, and hopefully do that fairly rapidly. I want to give Lawrence Friedel, one of my bosses who runs the Applied Sciences program at NASA, credit for most of these slides I'm going to be showing this morning. As Sabrina said earlier, I'm the ICESat-2 program applications lead, which means I support ICESat-2 applications at NASA headquarters. And I work with the program science and program executive, or the chief engineer for ICESat here. So let's see, I think I just click to do next slide. Does that work?
And if it doesn't work, you can just tell me to
Yeah.
advance the slides.
How do I advance? Yeah, go ahead. It looks like it's not responding to my click. Maybe
Okay.
I'm not doing it right.
Doing it right.
Thanks. I appreciate that, Sabrina. I'll just ask on it. So this slide just shows you how the Earth Science Division is organized through what it does. We develop technologies which then enable better application and work on orbit, which then provides. Initially, we were primarily about climate and other Earth science or system science research. We've since expanded applications you'll hear a lot more about today. All of that, of course, is underpinned by data science and computation capacity that allows the data to be processed and made available to researchers as well as applications users around the world. So those are and we've actually now organized the Earth Science Division at NASA headquarters into these sort of 5 baskets, if you will: technology, flight, research analysis, data, and applications. Next slide, please. Sabrina, thanks. So how we do applied science is it's all about partnerships. So thank you guys for joining today, your potential partners, just by your interest, and we hope you'll stick around and work with us on either ICESat-2 or some of these other missions you'll be hearing about, or other things. We work with folks across public sector, private sector, nonprofits, large scale to relatively small scale, global to state to regional. To relatively local. So partnerships is how we do our work. We fund these partnerships through generally competitive peer-reviewed solicitations, which come out traditionally through something called Research Opportunities in Space and Earth Sciences. Acronym is ROSES. It's an annual omnibus call that NASA puts out, which includes our applications calls as well as the research calls, etc. Increasingly, though, we're trying to find new ways to reach out to these partners through getting beyond ROSES, which frankly is a vehicle that folks in the NASA community, folks in other government agencies, folks I'd say in academia understand pretty well, but the private sector, nonprofits aren't as comfortable with it. So we're trying to find better ways to reach out and do solicitations with them and to build these partnerships. Our money goes to developing tools with satellite imagery. Of course, we are NASA with satellite imagery that can then help these partners make better decisions, do better regulation, take better action on behalf of their communities. Thanks. Sabrina, next slide. And these are the application areas in which we work. You can see each of these has a program manager like me that's in charge of it, maybe oftentimes more than ones. I work here at headquarters with a guy named Keith Gaddis, and we jointly manage ecological conservation, which is one of these areas you can see. We also have program in disasters, program in health and air quality. You just heard about from Laura, water resources, capacity building. Recently, we've added some new ones. Agriculture came in a couple of years ago, relatively new. Climate and resilience is new the last 2 years. Energy just getting up to speed now. Wildland fire is just getting started now. These are all separate programs in which we would put out solicitations or other calls for folks to propose to us and tell us how they can use our satellite imagery or other products for decision making. And then finally, mission engagement there is a relatively new position that says applied sciences will be working with these different missions like ICESat-2, of course, and others as they are developed within NASA to make sure that there's a strong applications presence in the mission from the get-go. We're not just waiting until we get on orbit and then figure out how to apply those data. Next slide, please. And this is some applications readiness levels, which we in applications or applied sciences at NASA borrowed from the Earth Science Technology Office, the ESTO folks who have long used technology readiness levels. These are applications readiness levels. And by that, we mean they're our way of tracking an applied sciences and applications project's progress, starting at just basic research. In other words, perhaps a research user has an idea that they think might work in an applied setting, or just anybody comes in and says, I think satellite data would help me do this. And so it's really just a basic idea, concept. So we start at those very low ARLs, and as you can see, we work our way up the ladder till the dream state, the goal for most of our work, not all. I mean, we do some feasibility, lower level ARL work that just stays at a lower level. But in many cases, our projects, we're shooting to get them up into the 8, 9 ARL levels, where we've developed a remote sensing based applications tool, and it's been turned over for operational or sustained long-term use by the partner, such that when the NASA funding ends, there's somebody out there that, hey, this is useful. I'm going to continue to do this, continue to support it, continue using it. That's an ARL 9. That's what that looks like in terms of partner transition and sustained use. And in many cases, that's where we want to get to with our projects, but not in all cases. And you really have to just look at the solicitation or the vehicle for the funding to say, what's NASA really trying to get out of this? Usually we'll be very clear in that vehicle. We're looking to get you up to, we're starting out here at 1 and we're looking to go to 4 or 5, or we're starting out at 4 or 5, want to get up to 7, 8, 9 in the call. So you'll know sort of what we're looking for. But this is the whole thing here, the whole ladder. Next slide, please. We've just come out with an online Earth Science Applications Guidebook. I want to recommend this to you folks. I don't know if you have time to scan that barcode, but if you can remember, appliedsciences.nasa.gov/guidebook. That's where you'll find it. It's online. We don't print these. The thought here is to provide folks who may not know much about NASA or NASA Applied Sciences with an on-ramp to approaching NASA to get a sense of how we do applications work here, what types of things we're interested in, what types of questions we ask, and how to interact with us through the voices and texts of our past users who've had successful projects with NASA. So, how did you do it? How did it work? How did you make the initial contact? How did you climb that ARL ladder with NASA? What types of things is NASA interested in doing? So it's sort of a soup to nuts online place where you as a potential user, or even you as an more experienced user, can go and hear the stories, learn from those who've climbed that ARL ladder themselves about how we do applications at NASA. It's a really useful tool. Recommend it to you highly. Again, appliedsciences.nasa.gov/guidebook. Check it out, please. Next slide. Want to call out the early adopters program. That's one primary tool that we use in terms of getting new people into working with our missions. We're a space agency, right? We're NASA. We build things, we put them on orbit. So that means we're a mission agency. So we want to align our applications work with the missions, as we're trying to do with this ICESat workshop today. And so one way we've done that, and actually Sabrina Delgado has been really instrumental in developing the framework for early adopters, is we bring people in early before launch to use simulated, in this case it would have been ICESat 2 data back in the day when we started early adopters before launch, to get them using simulated products so that we're ready when launch happens. There's already a user community that sort of understands the data, understands its potential, and actually has uses for it locked and loaded, ready to go. Back in the day when I started in applied sciences, it was very much about, we build these missions, Woody, just to do, basic research. That's really what they're about. If you want to do applied sciences, come see us after launch. We'll figure out how to sort of work it and make it happen. Then we came to find out that, that's not really a good way to bring applications on board. You got to start planning for the applied work just as the same time you start planning for the basic research that used to drive these missions. What we've seen over the last decade, and it's really instantiated in an administrative guidance document from Michael Froelich back in 2016, we're now treating applications on more or less equal footing with basic research as a rationale for missions and mission development. So we're involved, applications involved in the mission life cycle from even before phase A, even before we start really formulating that mission. So good news. So ICESat 2, as I say, I had one of the first early adopter programs. I think SMAP was first, maybe ICESat 2 was second in terms of our missions with early adopters. They had most of those early adopters, once we got ICESat 2 launched, became early users, or applied users, sorry, is the term we use now. And from those 24 early adopters, we now have 29 applied users. So we've continued to grow that community. These are intense relationships with NASA, one-on-one, where we work with them to make sure they understand the data and that we help them to put the data into their user decision-making frameworks. Next slide, please. And this one, Sabrina, thank you for this. This is just talking about where we're going with ICESat 2 in the coming years. As you guys know, ICESat 2 has been up. It's now going through the senior review process, or will be, whereby we look at missions that have met their minimum life cycle requirement or expectation, and give them a review whether or not to continue them on in the future. Generally, I think ICESat 2 has passed through these easily with flying colors, but just a testament to the value of ICESat 2 data. So as we go forward on the application side with an active mission, here's some of the things we're going to be working on. Again, Sabrina will be probably the lead for much of this. Continue expanding awareness of ICESat 2 and building capacity for its use. Welcome to this workshop. Thank you, Sabrina, for pulling it all together for us. Number 2, share lessons learned on early adopter program. The early adopter program has actually become something now that's standard across most all missions that we get spun up. They want to do early adopters, frankly, because ICESat 2 did so well. Sabrina has been involved with some other applications project coordinators in drafting an early adopter manual, so that should be out very soon. So spreading the gospel, if you will, of early adoption. Number 3, encourage more applied user partnerships so we can grow that number from 29 on up. Again, hopefully today will result in some in the atmospheric sciences area, atmospheric applications area. And then finally, continue engaging applied users, tracking their progress, highlighting their milestones, just making sure we're helping them climb that ladder such that they are using the NASA data to its utmost potential, and it's really providing them the decision support or other applications they need. And then the final slide, Sabrina, is just, I think, a clip from the guidebook I mentioned earlier that just shows you, some of the questions that when we begin a discussion with the potential users, these are some of the things we talk about, and it's really a two-way exchange, a relationship, gathering trust, building trust over time. So, for example, what problems keep you up at night? What are some of your big issues? Can you tell me about what you do day to day at work? Very, basic questions. What information don't you have that you wish it is? So that's where we start the conversations with potential applied users, and we build from there just to understand their needs. It really has to be user-based, has to be co-developed. We can't tell you guys what you need our data for. Only you can. So we're looking forward to the workshop today, getting more of these discussions and some of the open periods. And thank you, Sabrina, for letting me talk at you. Sorry if I went a little long there.
No, wonderful, Woody. Thank you so much for that presentation. And I do want to encourage everyone to post their questions for Woody and for Laura via the Q&A pod. If you are not seeing it on your screen, you should be able to access it via the 3 little dots that you see with more. And so you can submit it there. Ideally, we will be monitoring all questions from that section. So next we have Tom Newman, and thank you so much again, Woody. So Tom, let me go ahead and give you access to the presentation here.
I actually don't have slides I'm going to speak to.
Okay.
I'm just going to talk. Thanks to Laura and Woody for getting us off to such a good start, and Woody for that context. You're right, Woody. We began our ICESat 2 Applied Sciences program not quite at the beginning of the mission in pre-phase A or in phase A, but it was in phase B, so it was fairly early on. One of the challenges with ICESat 2 and with applications in general is that we're a new kind of data product. Photon counting elevations are not something that a lot of applied users will have familiarity with. And so we knew early on that was going to be one of our challenges, to make our data products as usable and as useful to those communities. And Sabrina and Molly Brown and Vanessa Escobar before had done a great job of getting feedback from those communities about what would be most useful and how could we best serve them. A secondary challenge with ICESat 2 is that, yes, it's a new product, and convincing both researchers and applied users that it's worth taking the time to learn how to use ICESat 2 data and worth understanding it was a function of how long ICESat 2 was going to be around for. Certainly any new product takes time to learn. And if a mission is only going to be there 2 or 3 years, it may or may not be worth your while. Particularly when compared with some other atmospheric missions, like the Calypso mission in particular, which is going on, I don't know, 15 years on orbit by now, which is just a fantastic run. Fortunately, ICESat 2 is now in its 5th year of operations. We're 4 years and a month into nominal science data collection, and I'm happy to report that, at least as of this morning, everything is looking good. The instrument is healthy, the observatory is healthy, the data is flowing as it should. Our documentation is always has room for improvement, but by and large has proven to be useful for users to help get them started. And you'll hear a lot more about that from others. So I was just going to say thanks for taking the time to spend a few hours with us today, and hopefully we were able to connect you with some good data for your research and for your uses. Sabrina, that's all I was going to say.
Thank you, Tom. That was great. You're keeping us on time here.
That was my secondary goal.
So, any questions for Laura, for Tom, or for Woody here?
I see one from Santiago that I could take a crack at.
Please.
Santiago, there almost certainly won't be an ICESat 3, at least it won't be called that. The ICESat 2 data for atmospheric science, yes, there is the AOS mission, which, as I understand it, will have atmospheric lidars, and there's other folks on this call who are more knowledgeable. In terms of surface topography and precision surface measurements, possibly. Topography, whether it's vegetation or ice or what have you, was identified in the 2017 Decadal Survey as one of the concepts to be competed through the Earth System Explorers Call. And in fact, we expect that announcement of opportunity for those missions in the next month or so. So hopefully there is an ICESat 2 follow-on to continue ice elevation and tree canopy measurements, and there will be a follow-on to continue atmospheric profile measurements.
Perfect. Okay, so thank you so much, Tom. I guess one question for you in terms of the feedback that we received today from folks on what they would want to see from an atmospheric data product. What is the possibility of having this feedback, make improvements to the actual products as they are today?
We welcome any feedback, and some of the things are doable, like new parameters or better quantification of uncertainties. Some are less or undoable, like adding a second color lidar or adding polarization information. It's just technically we couldn't do that without bringing ICESat 2 back to Earth and re-engineering it. But we welcome whatever feedback.
Perfect. Thanks, Tom. And we do have a question from Dave Jones. Are products that are produced from ICESat 2 data available as web services?
Good one. I'm going to defer that to our NSIDC colleagues who serve those products and have been working on migrating those products to the cloud. Do we want to tackle that one now, or do we want to wait till this afternoon?
No, we can wait until this afternoon. Yeah, we're going to have, Dave, we're going to have a session at the very end where the NSIDC will be providing a talk on the tools and services at the NSIDC. So thanks again. Okay, thank you, Tom. And we'll go ahead and then move with Steve to learn all about the atmospheric data products here. Thank you, Steve.
Okay. Hello, everyone. I'm Steve Palm, and I'm the lead on the atmospheric data products for ICESat 2. Been working with the mission since the beginning, and also with ICESat, its predecessor. So I've been around a long time. So I'm going to bring up my slides, hopefully without problems. But first I have to share my screen, right?
Yes.
Okay. I know we practiced this, so I should be able to do it. Okay. Oh, I've got that terrible wheel spinning around saying connecting. Okay, what's going on? Aha, I think we've got it.
Yeah, now we can see your screen.
Yep. I just need to go to, whoops. Sorry about this. Aha, I think we're there.
That looks perfect. Thanks.
Okay, good. Okay, so as I say, I'm Steve Palm, and I'm going to tell you guys about the atmospheric measurements of ICESat-2 during this presentation. And I'd like to recognize my co-authors here, Christine Barbieri and David Hancock, both with SSAI, and they are part of the ASAS software team that takes the ATBDs that a scientist write and puts it into code. So without them, we couldn't do what we do. Yokui Yang, he's at Goddard, is a scientist that works on the data, and also Uta Hersfeld, the University of Colorado Boulder. Okay, let's go. So what is the atmospheric channel of ICESat-2? Basically, okay, as you know, or most of you probably know, ICESat-2 is an altimeter. So it's optimized to get high resolution measurements of the surface, but it also has what we call the atmospheric channel, and it produces backscatter profiles from the surface to 14 kilometers at 280 meter horizontal and 30 meter vertical resolution. And we use the 3 strong beams of ICESat-2. You might know that ICESat-2 has 6 beams in total, 3 strong and 3 weak, but the atmospheric channel utilizes just the 3 strong beams. They are about 3 kilometers apart. And one of the unique things about ICESat-2 is its closed loop boresight alignment system. And that is a first for a satellite LiDAR. And it's a big advancement because it keeps the laser beam in the field of view of the telescope, which causes or keeps the signal peaked up and makes the calibration much easier. So it makes my job a lot easier. The ATL09 data product is what I'm going to be talking about, and that contains the attenuated backscatter profiles at 532 nanometers, cloud and aerosol layer height, apparent surface reflectivity, blowing snow properties, column optical depth, and a lot more. On the bottom, what you see is one complete orbit of the ICESat satellite, and what is shown is the backscatter profiles in image form along that track. So you can see, the clouds at various altitudes and the surface down at the bottom here. And as I said, it's just a 14-kilometer window that we're able to get from the atmospheric channel. So what are the major parameters on the product? Okay, we're up to version 5 now. We're working on version 6. The ATL09 files are in HDF5 format. and they're one orbit in length and contain about 141,000 25 hertz profiles. And the data are available at NSIDC online. But what is listed here in the table are parameters, the most pertinent parameters, I would say, for an atmospheric scientist. There's a lot more in ATL09, but these are the ones that are most useful for the atmosphere. So we have in the column to the left the ATL09 parameter, CAD-PROF. It stands for calibrated backscatter profiles, 0 to 14 kilometers. The resolution column is listed there, 280 meters horizontal, 30 meters vertical. And we have an accuracy column over there. 10% is about the calibrated accuracy of the profiles. And you can go down through. We have density from pass 1 and pass 2. This is from output from Uta Herzfeld's DDA, the density dimension algorithm. We use that to obtain layer boundaries of clouds and aerosols in the data. And we also have layer top and layer bottom. We have a cloud aerosol discrimination algorithm. So we have both clouds and aerosol heights on the product. We have layer integrated backscatter. So the backscatter within each layer is basically summed up, and that's related to layer optical depth. We have column optical depth, and that's based on what we call apparent surface reflectivity. And that gives us a measure of the total column optical depth of the atmosphere. We have apparent surface reflectivity, which is basically a measure of the received energy divided by the transmitted energy. And so that obviously is related to the total column optical depth. And we use that to actually derive the column optical depth. We have ASR cloud probability. We have a way of using the apparent surface reflectivity to detect clouds. We have a clear true, which is the clear sky surface reflectivity. And we have blowing snow, height and optical depth over any ice covered or snow covered surface. And we have diamond dust, which is a new parameter to, I believe, to version 5. Diamond dust, or what's also called clear air precipitation, is on the product. Okay, the next slide. I think one of the best ways for you to get a feel for the data is to show images and maybe compare with Calypso. A lot of people are familiar with Calypso. As Tom Newman said, they're into like their 16th year. But Calypso will finish up by fall of 2023. So ICESat-2 becomes one of the only lidars in space for these type of measurements after Calypso finishes. The top panel is Calypso. This is from a crossing of the two instruments. The orbits are different, but sometimes, or often they cross, but sometimes they cross within a minute or so of each other. And this is one such example of that over Australia. The top panel being Calypso, and the bottom panel being ICESat-2. So you can see the aerosol. We probably have, this is elevated aerosol over here, possibly smoke or dust. And we have the boundary layer aerosol here, which is also becomes stratocumulus over here. So all the features are the same in the two images. And we can see that ICESat-2 is probably a little bit better in terms of signal to noise than Calypso is, at least at night. We use these type of data. We have other crossings as well to check on calibration. And this is done by plotting the signal, the average signal at the crossover point with respect to molecular. If your system is calibrated well in clear air, like we have above, say, 10 kilometers, the average signal will follow molecular. And from the graph on the right, you can see the green is the Rayleigh line. ICESat-2 is red. Excuse me, Calypso is black. So we're very well calibrated in terms of the molecular signal, and also we are obtaining the same measurement that Calypso is as well. So these crossings are very, very useful. Another thing we did shortly after, or about a year after launch, was put the cloud physics lidar, which we have in our group. It was under Matt McGill, on the ER2, and we underflew the ICESat track. This one was just off the coast of California, where we had smoke from some of the fires in the region over California, was effecting out over the ocean. And the top here is ICESat-2, and the bottom is CPL. So CPL, being on the ER2 at about 65,000 feet, obviously has quite a bit better signal to noise, but we're seeing all the features in ICESat-2. This is the coincidence point when the two actually were aligned, both spatially and temporally. And this is a 10-second average signal, similar to the plot we saw before here, where we have Rayleigh is black, ICESat-2 is green, CPL is red, and we see very good calibration and correspondence with CPL. The layer detection is done by the density dimension algorithm that Uta Hersfeld has developed, and it's a great routine, a great algorithm that does not require calibrated data. All other uses of lidar data that I know of would always obtain layer boundaries based on calibrated data. But I did not know before launch how well I could calibrate this stuff because of its unique characteristics. So when I saw Uta's algorithm presented, she has different flavors for ice and ice and snow and whatnot. And at one of the meetings, I said, "Well, this could be used for cloud detection." And so with her help, she's developed that capability. And this picture here shows backscatter from ICESat-2, with the white lines are the boundaries, and that's what we want to find for layer top and bottom, and that's all from the DDA. So that's all working very well. Some of the things we've done comparing ICESat-2 with Calypso was to look at a month or a few months of cloud fraction, which is shown here. Calypso on the left, ICESat-2 on the right. So this is for November of 2018. And, you can see very good correspondence between the two, especially in the areas outside of the tropics. In the areas inside the tropics, you do have quite a bit of differences. And that's due to the fact that ICESat-2's window is only 14 kilometers. And a lot of the tropical clouds make it above 14 kilometers. So we missed some of that. And that's shown here, the global average 64% for ICESat-2, 71% for Calypso. But other than that, the comparison is quite good. This is a display of the same thing in a different way. Here it's a zonal average as a function of latitude, where you have Calypso as the green cloud fraction. And here you can see that big difference in the tropics that we saw in the prior slide. And but if you look at the Calypso cloud heights below 14 kilometers, that's the red line. So you can see how much better it aligns with the ICESat-2 measurement. So that's what's happening there. Outside the tropics, agreement is very good. As I mentioned at some point, we have the ability to detect clouds from the DDA algorithm, which uses the actual backscatter profiles, and also by apparent surface reflectivity, or ASR. So this is a comparison of the DDA on the left for a month of May 2019, and the ASR method for the same month. So you can see, if you look here carefully, how similar they are. They're not exactly the same. This cloud fraction globally is 67%, and over here it's 63%. So you do pick up more clouds by the DDA than you do by the ASR method, but it is still a viable way to get at cloud cover. This is Calypso ICESat-2 aerosol fraction. As I said, we have a cloud aerosol discrimination. So we find the layers, we then say, okay, or we separate out the clouds from the aerosol. And this is a Calypso ICESat-2 comparison from November 2018 again. And we see the spatial patterns are similar. But we do have you have more aerosol in Calypso than you do in ICESat-2. So we've been working to improve upon that cloud aerosol discrimination. And so that's one of the things that we're working on. Okay, one of my favorite things is Antarctica blowing snow and clouds. So Calypso, this is a pass over ICESat-2, and these are the typical clouds you see over poles, both the Arctic and the Antarctic, where they're very optically thin ice crystals. Some of this is what we call diamond dust, and also at the surface or near the surface, you get blowing snow, which is prevalent, I think, through this whole pass over Antarctica. It's where these thicker white line, where it looks to be the ground return, but it's actually a return from the blowing snow. Where that's thicker is where you have blowing snow. This is a blow up of this area down here. And that's what the blowing snow looks like. It's typically 100 to 200 meters thick, but it's very, very prevalent over Antarctica. I've done some work with Calypso to look at that climatologically over the Calypso lifetime. And Calypso had this large, it only went to 82 south and had that large hole. ICESat-2 fills that in, as you can see, inside up to 88 south. And this is the blowing snow frequency from ICESat-2. And we've done this for the 4 winter seasons, April through October, that we've gotten from ICESat-2 2019 through 2022, showing you the blowing snow frequency. And what really is amazing to me is the lack of interannual variability. It's really steady from one year to the next in terms of the frequency and the spatial pattern. We've recently done PBL height retrievals from ICESat-2 data, paper we published last year. And this shows you the boundary layer height. Red is 4 kilometers over, the desert regions, Southwest US, and, you have, lower heights over the oceans, obviously. But this is one area where ICESat-2 could maybe contribute to the air quality, because most of the pollutants, or all of the pollutants, are trapped within the PBL, and so knowing its height is very important for modeling and transport of pollutants. Here we have an Australian fire from December 2019. MODIS is on the left. This is Australia, the smoke being ejected off the coast. And we have the ICESat-2 pass coming down through here with the backscatter shown on the right. And this is the smoke. This whole area here is the smoke coming off the continent. Another good example for ICESat-2 would be volcanoes. Volcanic eruptions occur quite often, as you know. This one was from April 2021 in the Caribbean, St. Vincent volcano. And we see inside the circle, this is the part of the volcanic plume. The vertical information of where it is, of course, very important for aviation. We can track the plumes from passive satellite measurements, but we don't know the vertical distribution until we have an active system like ICESat-2's lidar. Now, I'd be amiss if I didn't also talk a little bit about some of the challenges with working with ICESat-2 data. And beyond the fact that it only has a 14-kilometer window, we have this thing that I call folding, okay, where when you have a cloud above 15 kilometers, it will actually show up down below in the lower region. So where this circle is, okay, these returns down here are actually from above up here. These are actually from 15 to 17 kilometers. So you can see the cloud up here. It looks like it got chopped off, right? Well, it did. And its top is then actually folded down to the lower portion of the backscatter profile. So that has to be, it's important to recognize when this happens. And, we have a flag for that. And for instance, when trying to get the boundary layer height, like over here, this is straight marine aerosol right in through here, you have to know, well, this is not the boundary layer, this is a folded cloud. So recognizing when folding happens is very important to the data analysis. The other thing about ICESat-2 is its day-night difference in signal to noise. Because ICESat-2 uses a high repetition rate laser, the background noise scales with the laser repetition rate. And so the daytime data shown in the upper right for ICESat-2 is not nearly as nice, or I should say the signal to noise is much less than it is at night in the lower left. And this is a pass off the coast of Africa showing Saharan dust inside the circle here. And this is a nighttime pass. The prior day, this is a daytime pass in the same region off the coast of Africa. And there is dust here, but you really can barely see it. It's buried in the noise. So, this shows you, a problem with the data in that if you're doing diurnal studies, you have to recognize you can't get the same resolution at nighttime at daytime as you can at nighttime. And so those are the two big problems, I should say, three big problems: 14-kilometer window, the folding, and this difference in day-night signal. So what we're working on now for the next version is we want to have a layer optical depth, which we don't have at present, each layer given an optical depth. We want to improve that cloud aerosol discrimination, and we want to improve the thin layer detection in the DDA. And I'm confident UTA will be successful in doing that. We want to add cloud phase and aerosol typing to the product. And as far as the data availability, we have the version 5 products out there at the NSIDC from October 2018 to August 10th, 2022. Version 6 is currently being worked on and probably will be available sometime next spring. And we have a quick look image site, which is there. And I will be talking a little bit more about that later today and giving you some examples of how that can be used. And just to let you know, this is a good paper for an overview of the atmospheric data products that was published last year. So I think that's it. Yep, that's the last slide. I thank you for your attention, and I welcome any questions. And you can get a hold of me at any time, and I'd be glad to help with the data or its interpretation.
Thank you, Steve. And as you mentioned, we are going to get a little bit more in depth into the data products as we move through the webinar. But we do have just two questions that I'll take. We are into our break time. So we have a question from Randy Bass. Sorry if I missed it, but what is the current latency of the ICESat-2 data?
Yeah, the current latency is roughly 3 days. If you go to the when we go to the website later, I'll show you that the fact that we have data there from 3 days ago, and the latency is rather large, but that has a lot to do with the data volume and the nature of the mission being an altimeter, and you have to. I know they have to know the pointing, the exact pointing, and position of the orbit and all that. And so it's mainly that 3 day. It doesn't have anything to do with the atmosphere. It's mainly the altimetry that determines that latency.
Thank you. And there's another question from Dave Jones. Steve, thanks for your presentation. Can you discuss the data latency for ICESat? You just discussed that. Is any of the data being used by NOAA to assimilate into their models? Thanks.
No, not at the present, and mainly that is due to the latency problem, I think. But for like reanalysis and stuff, I guess it could be used, but at this point, it is not. And that's one of the objectives of our meeting here today, is to try to get more use of the data. So, but no, the answer is no.
Thank you. And I'll just take one more question. So okay, regarding the better SNR at night, why does laser repetition rate vary between day and night, resulting in the higher nighttime SNR?
No, the laser repetition rate does not vary. It's constant. What I was saying there was that the background itself, okay, for a LiDAR system, is proportional to the rep rate of the laser. But the laser rep rate does not change. And so at nighttime, obviously you don't have background, right? But during the day you do. So you get a lot of background. If you go to Calypso, Calypso is, I don't know, 20 hertz. So they get, every second, they get 20 snapshots of the background, right? Where ICESat-2 gets 10,000 snapshots of the background. So that's why, the background magnitude depends on the laser repetition rate.
Thanks, David. Yeah, that was a question from Woody. Sorry, Woody.
Okay.
Couldn't see your name. Okay.
Yeah,
and
thanks,
so-
Steve. So the background equal photons equal light, right? And when you say background in this case,
Yeah.
you mean it's light. Yeah, the sunlight.
Yeah.
Photons.
Yeah,
Gotcha.
sunlight.
Thanks. Just making sure.
That's right. Just sunlight. You're right, Woody.
And Tommaso is asking, I might have missed this. What is the vertical resolution of your products?
I'm sorry, 30 meters.
Okay, perfect. I think we are into our break, so I'm going to stop there, and then we'll respond to your questions via the chat. So I had asked for the questions to be sent through the Q&A, but we can go ahead and monitor the chat instead if that works better for folks here. So let's come back at 11:40, and we will continue the conversation then. So thanks, everyone.
Okay. Thank you.
Hi, Ute. Oh, I
Hi,
can't hear you.
Sabrina.
How are you?
Good. How are you?
Good. So I just put us in a practice session in case you want to pull up your slides.
Sure. Yes. Do you want? Let's see. Share
Perfect.
is.
And I introduced to everybody at the very beginning, but I can just go ahead and say again what are sort of the goals and for this session, and then just let you take it away.
No, now it shares everything.
Yeah, it's sharing your screen there.
Yeah, but it shares too much. It shares anything you have in preview. So just close everything else. Now it's just my
Yes.
session. Does it?
Can
Yeah,
you
right?
make it? Yeah, yeah. Although I can see the next slide, the title of the next slide. Do you want to, is there a way for you to increase it?
Well, I can, but I still want to. I want to be
Oh,
able
there you
to
go.
see the
There.
meeting. Let me see whether it advances. Yeah, now it goes by slide.
Yes.
Sort of. Not quite. Okay.
No, I think that works.
Does not do this very properly. Like if I go into slideshow, do you want to try to go into, if I go into slideshow, right?
Yeah.
Then I don't see you anymore. See, now it goes into full screen.
Oh, there you go. Yeah.
This is better.
Yes, I think that's better.
And I still see you a little bit. Okay.
Well, that's good.
Let's
In my
see.
layout, I don't know, I have everybody on the top, and I'm assuming that everybody sees what I see, so I'm not really sure.
Yeah, they
This is
should.
Andrea. It looks good to me, the screen.
Hi, Andrea.
Hi, Andrea. Yeah, we're taking votes here on how to do this. Okay, I think it works. I can see a little bit of the panel actually in the corner.
Yes,
Like
I can see that
Sabrina and
too, but
Andrea and Steve.
yeah, I don't know if you would be able to get rid of that.
No, I want to.
Oh, okay.
That's why I usually don't share full screen, because some apps will dump away the meeting, and then if someone has a question, you have no clue. You just sort of speak into the void.
Okay. Yeah, well, you know, it has been an interesting process with WebEx so far. We'll see how it moves forward.
It works all now, but hey, it would not let me in this morning.
Yes, it was asking for registration IDs, and those should have been sent automatically. I spoke to somebody
I
this
had
morning as
IDs,
well.
but it wanted a password, and
Yeah.
I didn't find a password.
Yeah, yeah. I'm happy you were able to get us an attendee and that I was able to move you up.
Yes.
So,
Okay. Yeah.
Sabrina, sorry to interrupt. So real quick, are we sharing this session? Are we sharing our own screen then?
Let's do that. I think that's going to work better because I tried, you know, granting access to Woody and to Laura, and that didn't seem to work very well.
Okay, that works
For
for
some
me.
reason, I'm not sure why. We had practiced everything.
Well, I think this is going amazingly smoothly. I know you have some glitches on your end, but from the side of just listening, it's been fantastic so far.
Okay, great. Oh, thanks for the feedback. Yeah.
You're here, Steve. You were fantastic.
Okay, so I think we're 1 minute away, so I'm going to end the practice session here. And then I'll just introduce you, Ute.
And I just leave everything as is.
Yep.
Yep.
So,
Right.
Uta, oh, hi.
Hi, Steve.
Hi.
I think we're going to go ahead and get started. So
Okay.
thank you, everyone, for coming back. So next, we're going to have our plenary talks, and this will be focused on an in-depth look at Calypso, at ICESat 2, again, for the atmospheric data product, as well as AOLIS, and maybe a little bit about EarthCare and AOS. So our first speaker is Ute Hersfeld, and she's from the University of Colorado Boulder. So please take it away.
Hi everyone, thanks Sabrina for the introduction. So following Steve's great primary talk on the ICESat data products for atmosphere, we'll take a little bit of a closer look in my talk, and specifically with an eye on what types of applications can we envision for ICESat atmospheric data products, and those are just the ones we see. I hope people in the meeting here will have some other ideas. The talk's co-authored by Steve Palm, my grad students Adam Hayes and Huilin Hahn, by Dave Hancock and Christine Barbieri, who implement the code at NASA Goddard Space Flight Center. And since we'll speak a little bit about Calypso in comparison, in the end also by Mark Vaughan, who is the lead of the Calypso algorithm development team. Okay, so the focus here is on applications of especially tenuous layers. So these are specifically thin or faint layers, including both aerosols and clouds. So Steve already had examples of both of these. The information on tenuous atmospheric layers is first important for estimation of heat flux in the Earth atmosphere system, and that in turn is essential for modeling the Earth's climate. So if we don't have enough data, there are misprojections of the climate at present and going forward. Of course, if we can't detect layers, we can't classify them and so forth. A second big area of applications is that information, especially on faint aerosols, is important for environmental health and safety. For air quality and pollution, we can utilize ICESat data to monitor fires and volcanic eruptions. Some aerosols affect transportation safety, such as those from big volcanic eruptions, which can lame the aircraft transportation for months, and their applications in weather forecasting. So if we miss the really faint layers, especially during daytime, but also during nighttime, then that leads to errors in estimation of the optical properties of clouds and aerosols. And then that in turn results in other downstream errors in the data or information stream that we could derive from the atmospheric LiDAR data. Okay, so what are actually tenuous or faint atmospheric layers? So here are some examples. For instance, thin cirrus clouds at any latitude. You'll probably know that if you're out on a hot day and suddenly this really barely visible cirrus moves in, there is a significant drop in temperature. And so that is a modulation of the heat flux. Then especially at the tropics, there are also sub-visible cirrus clouds, which bring a similar change in heat radiation from the Earth to the atmosphere. There is blowing snow and diamond dust, as already explained by Steve, and these are mostly features in the higher latitudes, Antarctica and the Arctic. They are also occurring in mountainous regions. There are faint aerosols, including smoke plumes, Saharan dust, of which Steve already gave an example, Asian dust, which is kind of more difficult to detect than Saharan dust because it's injected higher into the atmosphere, so it'll leave some of the ICESat data. And it's more diffuse. There is volcanic ash, as I already mentioned, such as in 2010, the Eyjafjallajökull in Iceland erupted, and that disrupted air traffic throughout Europe for over 2 months. All these have in common that they're weakly scattering layers that are hard to detect, especially during daytime conditions. Okay, so here's some basic information on the ICESat atmospheric data product. The Atlas sensor board ICESat is a multi-beam micropulse photon counting LiDAR, which means it records returns from every single photon in the 532 nanometer, that's green light band of the sensor. And yes, mostly that's background, but there are also a bunch of artifacts which have to do with the instrument properties. The ICESat-2 atmospheric data are telemetered, which is sent down to Earth from the satellite as 400 shot sum data, which results in a long track resolution of 280 meters and vertical resolution is 30 meters. So they're not recorded photon by photon as are the ground data. The ICESat-2 atmos data range from 0.5 kilometer to below to 13.5 above the Earth's surface, defined by the onboard DEM. All the data are publicly available on the Earth data site operated by the National Snow and Ice Data Center, and there they're updated every 6 to 12 months. You then want to search for ADLO 4, ADLO 9, 16, and 17. We'll cover each of these data products in separate talks throughout the day. There are now rapids available, which Steve has already illuminated too, but there will, I see, also be a training session on how to find stuff. The types of data on tenuous layers available on the products will be a bit more clear, I hope, following the next slides in this talk. Now, if you really want to know what we're doing, there are the algorithm theoretical base documents where the algorithm is described more detailed than you ever want to know, like mine is over 400 pages by now, and so forth. However, all this stuff is publicly available following NASA's move to open science. So definitely there is the description of the source code if you're so inclined to recode it. Okay, so we detect any layers, but especially tenuous layers, in the atmospheric data by the density dimension algorithm for the atmosphere. And here is sort of the steps. First, of course, we load all parameters we need in all the data, as you see on the top. Do people see the mouse? Maybe, maybe not. And so you can kind of see the background. What I want to point out is this is a transition of nighttime on the left to dusk, and then daytime on the right, which you can tell by the increased speckly appearance of the background. So then the contrast between the actual feature of interest and the background changes. Now we calculate a density field as a data aggregation method. And so the left and right are just different rendering using different colors to bring out different features. As you see in the left bottom, we get really bright returns, which are strong returns in the aggregation from sort of the centers of the clouds. And then in the next step, we use that to pull out part of the reflectors. So there is sort of a trick using density as a dimension. And the idea is you use mathematics stolen from neural network, but it's actually not a neural network. It wouldn't run fast enough for operational processing of all the ICESat-2 data. We use an auto-adaptive threshold function to separate atmospheric layers from background. And that actually allows it to work through day-night transitions, adapting to this backscatter, also to apparent surface reflectance, without hand-holding the algorithm. And then after the first pass, we get like just a little bit of cloud. Now, we want actually dense clouds in, so yeah, next we throw away all the speckles, which are junk, but we want dense clouds and faint clouds in presence of dense clouds, so all of these. So we actually run the density dimension algorithm twice, called pass 0 and pass 1, because that's how you count in Python. And we use a small kernel and then a larger kernel to pass different types of features. So in the second pass, you actually get a lot more features identified. Then you kind of combine these masks, but the trick is you can find strong reflectors in presence of weak reflectors, and you can find both adapting automatically to these challenges that come from the differences in backscatter during daytime and nighttime conditions. To a point, I mean, Steve showed you can lose the signal totally, well, then we're out of luck. You can, yeah, so then after all this is done and you have the cloud mask, which has the same resolution as the input data, so 30 by 280 meters, we then determine atmospheric layer boundaries. And we also have a confidence measure, as you see in the bottom, which shows you how certain we are that the boundary is the boundary. So the top is clear, but then if there's some variability, confidence drops. So you can use that as kind of a guide. After all this is completed, we do specific detection problems, like can we see the ground despite attenuation of the signal above it? Can we find diamond dust and blowing snow or Saharan dust and all these other things? Okay, so here is sort of a flow of the algorithm steps. You can mostly in this slide see how first we get little cloud, but then packing this away opens the ability to see the rest of the clouds. This is all described in a paper we have in JRL. And so here are the steps repeated that may not be as interesting for this community. Now here's some highlights of things we can do. We have, for instance, a typical night example on the left, and we have a daytime example on the right. So you clearly see the difference in clarity of the signal. However, we are able to pull out boundaries of stratus clouds, cirrus clouds, altostratus, and so forth, even in the daytime data with good confidence in the layer detection algorithm. Steve Palm's favorite is blowing snow and diamond dust, especially over Antarctica. And these are important for transport of snow because although it doesn't snow a lot in Antarctica, moving snow between areas is a big factor regarding mass of the Antarctic ice sheet. And so the red line shows blowing snow. Then blowing snow is sort of capped by 500 meters naturally, but there are features above it which are associated with diamond dust, which contains icy particles at even thinner density. And you can see how both are whipped along by the wind. However, diamond dust can also occur without high wind speed, while blowing snow does not. So we didn't think much of it, but actually ICESat 2 is to our knowledge, the only atmospheric lidar which can detect diamond dust. We can detect both together or separately. The other inset shows you where all these tracks are located. Here is another example of diamond dust. You can see it flowing along. So similarly, right, you first get not much diamond dust in the first pass, but then you get the entire field of diamond dust with different densities. And so the density field allows you further interpretation of the resultant data, and that is actually reported on the ADL09 data product. So if you want to play with it, you can plot all these various properties. Okay, so now Steve mentioned we have a challenge with Saharan dust. So we've actually been working on a new capability for the release data products, which will become available, I heard in spring, I thought end of this year. So what is Saharan dust? Well, aerosols from dust storms in the Sahara can be transported far around the globe. So they form these really far-reaching layers. For instance, in the figure we have here, this is 1,400 kilometers in one scene. So it's a big part of actually the track around the globe. These layers occur only below 6,500 meters and at lower latitudes. And now there has been a problem with reporting internal variability because after all, the DDA is set up to pick up small changes. ICESat 2 has this advantage of being a really high resolution sensor. But in this case, the goal was to suppress actually part of the internal variability. So we do this by implementing a conditionally implemented third density run, and whether we run it or not depends on the internal variability of the atmospheric layers as reported in the first 2 runs. Regardless of all this detail, now we have continuous layers reported as we should, and these show boundaries of Saharan dust layers. So that will be on the next data product. So that here are some characteristics of our results that may be relevant for the applications. The analysis retains the full resolution of the data sets, because you get asked, of course, hey, what's the resolution of the ICESat atmospheric data? Other than most algorithms implemented elsewhere, the DDA retains the full resolution of the data set. It facilitates detection of tenuous layers in presence of optically thick layers, so you can find aerosols among clouds. For instance, suppose you have pollution in an industrial area, you will be able to track those in presence of good weather or bad weather, simply speaking. The algorithm is sufficiently computationally fast, and so forth. I already said the other things. Now, Sabrina asked me to throw in a bit of a comparison with other data sets. As Tom Newman mentioned, the CloudSat Calypso mission is the main atmospheric lidar mission. It's been around for 20 years, nearing the end of its time. And there has been considerable development of classifications of Calypso data. Calypso data go to 40 kilometers, not just to 14, and it's a dual color sensor, so it's meant to look at atmospheric data. Thus, it has a whole bunch of advantages over ICESat, where initially the atmospheric data products were sort of the noise, hey, can we see the ground, although they're clouds. So despite of all the data development, there are a few problems of faint stratospheric smoke plumes missed in the CALIOP data, such as these. And they're only partly detected in the Calypso data. Here's a different example of subvisible cirrus measured over the Pacific Ocean in a 2007 data set. And you can see that by eye, you think there would be another layer, but there are blotches in between and there are gaps. Or here's the example of volcanic ash, in this case from this year's Hunga Tonga eruption. By eye, you would think there's a sort of semi-continuous layer, but there are lots of gaps. So now we actually have a planned solution, namely to adapt a density dimension algorithm for the CALIOP data. And in an example which I created for a proposal, actually, we put in some ad hoc version of such a CALIOP DDA, and you can see that using something like density 3, it is actually density 3, but implemented not like we do it for ICESat. We do find bits and pieces of this stratospheric smoke plume. So the plan going forward is now to actually implement a CALIOP DDA first as a research algorithm, but probably as an operational algorithm, because given the Calypso mission, it's nearing its end, there's still interest in detecting certain types of mist layers using more modern approaches than were designed and implemented, because after all, the mission was started 20 years ago. So not only do we have new sensors, we also have mathematical advances, and we have different computer powers, simply speaking, than we had 20 years ago. So that motivates an ability to actually go forward with modernized mathematics. So again, of course, the applied problem is the same. The information on the tenuous layers is important for the estimation of heat flux and for environmental health and safety, airline transportation and weather. Some of the examples are actually exactly the same. We need to add especially Asian dust, because Asian dust is more diffuse and goes higher up in the atmosphere, so we can't even see all that in ICESat. And recently, NASA funded our group together with Mark Vaughan and Kathleen Powell from the Calypso group a project to integrate this algorithm. Steve Palm's on that as well. Huilin is our grad student. And we will then, of course, when we have this all done, then we could look at a combination of ICESat and Calypso results and more applications from all of this. So to the applications community, we do take hints such as, hey, we really like this layer and we like this capability. That's cool. We also take hints in the form of, we would really like to see the following, and I think it's missed in the following data set, preferably with an example where you didn't quite see what you saw. Okay, so far so good. Thanks for listening. I include a bunch of references here just because in case Sabrina shares this, then you'll be able to take a look. That's it.
All right, wonderful. Thank you so much, Ute. That was a great presentation, and we will be taking questions after or during our discussion session at 1 p.m. So I encourage everyone to start maybe placing those in the Q&A, but I will give you the opportunity as well to voice your questions during that discussion. So next we have Jason Tackett, who's a research physical scientist for Calypso at Nassi Langley Research Center. And so Jason, if you want to go ahead and share your slides, I think that has worked best so far. And Jason, we're not hearing you currently. We can see your presentation, okay?
Ah, there's the secret button. Can you hear me now?
Thank you. Yes, perfect.
Wonderful, thank you. Okay, yeah, so I'll be giving an overview of Calypso-enabled applications. So when we talk about applications in reference to Calypso, what we're thinking here is how operational agencies use Calypso data for their objectives. And by operational agencies, I mean those with like air quality forecasting, numerical weather prediction, these sorts of things. So it's these operational agencies that I'll be addressing today. And there we are. Okay, so just a quick recap of the Calypso mission, just in case anybody doesn't know all the details. So it was launched in 2006. The satellite carries 3 instruments, the primary of which is the elastic backscatter lidar Calliope that operates at 2 wavelengths with a depolarization capability at 532 nanometers. Currently, the spacecraft is healthy and it's in operational acquisition mode. So right now, the limiting factor with the Calypso mission is the power. And so, as was mentioned a couple of times previously, we're planning to cease science operations next September. And by that point, Calypso will have 17 years of data under its belt, which is pretty good for what started off as a 3-year mission. The primary data products are profiles of attenuated backscatter at the 2 wavelengths. And here I'm giving an example from the California wildfires back in 2020. So the profiles are reported at both wavelengths with depolarization information. The resolution is 30-meter vertical by about 1/3 of a kilometer horizontal. Level 2 products provide layer top and base altitudes, along with information on layer type, cloud aerosol discrimination. There is aerosol subtype information, so Calypso can tell the difference between dust and smoke and other types. There's cloud ice water phase information, and then retrieve profiles of extinction. So there are 2 production streams with Calypso data. The standard production stream is the highest quality data. It has the most accurate calibration, the most sophisticated of our level 2 retrieval algorithms. And the latency is several months because it uses meteorological data from the MERA 2 model, which has a latency of a couple of months built into it. There's also an expedited production stream, which the calibration for that isn't quite as accurate, just by a few percent. And the level 2 processing algorithms are from a previous version of the data products, so not quite as accurate. However, it's still plenty good for understanding where aerosol and cloud layers are and these sorts of things. The latency is 12 to 24 hours. So even though it's intended for near real-time applications, it's usually too long for really tactical real-time applications. So someone fighting a forest fire, this is information wouldn't be too helpful. However, for data assimilation purposes and for some other reasons, this latency is still manageable for these for certain applications. But really, the main contribution that Calypso provides in terms of applications and to operational agencies is in the development and validation of products and tools that operational agencies use. And I'm going to give a bunch of examples of this. So we'll start off looking at aerosol assimilation. So some of the first assimilation efforts of Calliope was with the Naval Research Laboratory and their NAPS aerosol transport model. And so this model, it operationally ingests MODIS AOD. And so experimentally, researchers there found that if they assimilate Calypso data as well, that helps understand how the aerosol should be distributed in the vertical. And when they do this for the initialization, they find that their 48-hour forecast is improved of where they predict aerosol optical depth to be. There's also some assimilation experiments at the ECMWF that was spearheaded by Angela Benedetti using a couple of Calypso products. After she working on these assimilation experiments, she also used Calypso to help build the infrastructure for assimilating Aeolus data into ECMWF models for aerosol applications. So this is a nice example of Calypso assimilation into the NICAM Sprintars model. So here these researchers ingested or assimilated Calypso extinction profiles into the model, and then found that the deviation between forecasted extinction and what Calypso ends up actually retrieving in the following month improves by the assimilation of Calypso data. So there's been several compelling studies done showing the benefit or the opportunity for aerosol assimilation with Calypso data. To my knowledge, I don't know, believe there's any agencies that are operationally ingesting Calypso at the moment, but over the years, there have been many cases, experimental studies showing the potential there. So Calypso, because it provides information on an aerosol type and the vertical distribution, it's actually really helpful for validating plume heights from different models. So these are two different efforts by NOAA researchers evaluating the plume heights from the high split model, and in the second case, evaluating the movement of smoke within this GEFS aerosol model from a wildfire. So Calypso data has also been used to evaluate the smoke plume injection heights by the EPA CMAC model in this first example here. And they did this in a really clever way. So they used backward trajectories to connect Calypso smoke observations to MODIS fire detections upwind. And by doing so, they were able to come up with an independent estimate of the smoke plume injection height that they could compare against the model, which is pretty clever. And the second example here by Yao et al., this is really neat. So they use machine learning and Calliope observations along with near real-time information on fire activity and meteorology and geography to create a predictive model for the minimum smoke height of a plume from a fire, and then the risk of the exposure to the population downwind. And really, this kind of speaks to that idea of the integrated observing system that was discussed earlier in talks today. The combination of satellite and modeled information really becomes more powerful once you integrate everything together. Calypso has also been used for evaluating air quality models. So in this first example, these researchers used Calliope extinction to validate aerosol dispersion over China from this RAMS CMAC coupled model. And what they're able to learn from this analysis is that the differences that they saw in the model predicted extinction, aerosol extinction, and what Calypso observed was likely attributed to how the model was handling hygroscopic growth of water-soluble aerosols. The second example, so Calypso was used to evaluate planetary boundary layer heights that are predicted by the WRF model. So this was done as a part of a report by the Ozone Transport Commission, which is a multi-state agency working in the northeastern United States. And the goal of this this group is to identify ozone-related issues in their region and then communicate that to the EPA. So in their study, they used Calypso to derive their own PBL heights and compared this to what WRF predicted as part of the analysis. Last example here, so NOAA researchers use Calliope to understand the biases in their smoke forecasts from this real-time air quality monitoring system. So this system, it operationally ingests MODIS, and what it'll do is, for a smoke, is it'll typically put smoke squashed right in the planetary boundary layer. So through this analysis, they were able to see that using Calypso, if they distribute the smoke according to Calypso observations vertically, then that improves their smoke forecast. Okay, so we've also identified at least 3 agencies that use Calypso data for exceptional event analyses. So an exceptional event is when the local airborne pollution levels exceed the national ambient air quality standards. And so what local agencies will or have to do is they have to prepare a report showing where the pollution came from and see if it came from outside their government's jurisdiction or not. So there's at least 3 agencies who use Calypso data for that. Calypso data is also made available through the EPA's Remote Sensing Information Gateway. So this is a visualization tool that allows air quality analysts to look at satellite data, model data, surface data, all in one platform to help in their work. So moving on to aviation safety. So in our conversations with the Darwin Volcanic Ash Advisory Center, you know, the main thing they're trying to do is come up with aviation hazard forecasts within the next few hours. So the latency of Calypso products, you know, is kind of prohibitive for that. They typically use geostationary satellite data that's available, you know, rapidly for their forecasts. However, they do say that they'll use Calypso expedited imagery for post-event analyses to understand how well their forecasts did. Another way the Darwin VAC has used this information is to evaluate the Australian Bureau of Meteorology's access model, or it's a suite of models. So the Darwin VAC uses the access model to get meteorological information, and they use that in conjunction with high split trajectories to develop their ash mass forecasts. So in this study, they're able to use Calypso ash detections to understand or to verify their forecasts and the altitude and these sorts of things. There have been a couple of larger studies that you've used Calypso data as a validation source for airborne hazards. This first one was a 3-year study that the goal of it was to close the gap in data that's available to European disaster response agencies for airborne hazards. So what they did is they used Calypso data as the validation source to evaluate volcanic aerosol height retrievals from a whole slew of passive remote sensors. And in a similar way, this scope nowcasting project, it's a WMO sponsored project that also uses Calypso for validation data. Similarly for to evaluate passive height retrievals. Calypso has also made a contribution to validating aircraft icing products. There's a product called Dardar that's a merger of Calypso and CloudSat information that's produced by the CloudSat group that they've been used in several studies to evaluate these aircraft icing products that are distributed by the National Weather Service and the NOAA's Aviation Weather Center. So for numerical weather prediction, Calypso actually provides a really good validation source based on the cloud observations that Calypso provides. So, and then the top bullet here, Calypso cloud observations are used for developing retrieval algorithms. And these 2 studies, the first one uses, the know-it-all, uses Calypso cloud retrievals as a training data set for probabilistic retrieval algorithms for cloud masks, ice water phase, and so forth. Whereas the Min et al. Study uses a combination of machine learning with Calypso and Himawari observations in order to improve the Himawari retrievals of cloud layer detections. And in doing so, they're able to better detect faint cloud layers in Himawari retrievals. Calliope cloud observations are also used for validating atmospheric motion vector height assignments. So these atmospheric motion vectors are the way that you retrieve winds using geostationary passive instruments, where you look at the motion of clouds over time and you can determine the direction and speed of the wind. And so in several studies, researchers have found that if you use Calypso data to assign the height of that atmospheric motion vector, in other words, where the height of the cloud is, you can improve the retrieved wind speed afterwards. And lastly, Calypso observations are used to identify biases in these passive operational satellite data products. In the first case, the Huang et al., they were able to identify biases in cloud top height retrievals. Whereas in the second reference here, they found that they're able to find cold biases and retrieve sea surface temperatures due to undetected clouds in passive remote sensing retrievals. It's important to note that these retrievals that we're discussing here that are being improved all ingested operationally into numerical weather prediction models. So this is a nice benefit. Okay, so that kind of wraps up the examples I was going to go through. Sabrina asked to say, where does types of situations does Calliope struggle in? This is kind of adds more to what Uta mentioned previously. Calypso struggles to detect optically thin aerosol when there's a really high albedo surface in the daytime. This example is a ground track over the deserts of Australia in the daytime. And on the left-hand side, you can certainly see an aerosol layer from 5 kilometers to the surface, no doubt. But on the right-hand side, the feature detection doesn't quite detect at all. And this is due to the just the fact that the surface is really scatters the sunlight strongly, which degrades the SNR and gives lots of problems with the retrieval. This exact same overpass in the nighttime would have no problem detecting that full extent of this layer. This is a kind of a peculiarity or a challenge with Calypso observations. And in the aerosol subtyping algorithms, Calliope has a hard time telling the difference between smoke and urban pollution. So given the observables that Calypso has, smoke and pollution look pretty much the same. You can't really tell the difference between the two. So in this example on the right, this is smoke over Southern Africa, and all that orange stuff at the very bottom is classified as polluted continental / smoke. That's because we're saying that tells you that it's a mixture. It could be a mixture of pollution and smoke, or it could be one or the other. There's just no way to know. It's only once that the aerosol, the smoke layer gets elevated above the planetary boundary layer that we can say, oh, well, something must have put that up there. It was likely a fire, and therefore it's most likely smoke. Anyhow, so this is a challenge in the retrieval algorithms. So I'll just summarize some up here. So like I was saying before, the primary contribution of Calypso is for validating and developing tools that are used by operational agencies. And amongst all the information that Calypso provides, really it's spaceborne LiDAR provides in general, is the vertical layer detection information is extremely valuable, and the ability to discriminate between clouds and aerosols it stands out as some of the most valued assets for applications. I'll stop there. Thank you.
Great. Thank you so much, Jason. And as a reminder, we will be taking questions during our discussion session at 1. But it is wonderful to see all of the great applications that Calypso has. And I think the hope here is that we will have similar applications for ICESat one day. So next, we're going to move to a presentation by Jonas von Bismarck from the European Space Agency. As I mentioned at the beginning of our focus session, he's the AOLIS Data Innovation and Science Cluster Technical Officer. And we're also joined by Tommaso Perinello, who is the Aeolus and Cryosat ESA mission manager, and Thorsten Ferrer, who's the head at the atmospheric section at ESA. So thank you all for joining us today. And if you can share your slides, that'd be wonderful. We can see them. Perfect. And let's do a sound check, Jonas.
Now it should work.
Yes,
Can you hear
wonderful.
me? Sorry, yes, I'll keep the video. I'll keep the video out, right? Or do you want me to turn it on?
Whatever you prefer. It's always nice to see a friendly face.
Okay, no, sure. Yeah, thanks. So I hope that you are seeing the right version of the presentation in the right mode, because I kept the other screens on. As long as it's working, I'm
It
gonna
looks
go
great.
ahead.
Yeah.
So it's a great opportunity for having us here and being able to present the Aeolus mission and its products. And so let me just go ahead. So I'm giving this obviously on behalf of the whole team, and I'll also show a few slides on a potential Aeolus follow-on and EarthCare later on. Just see why I can't go ahead. Now it is going ahead. So of the three big programs of Earth observation satellites that ESA is involved in, and this is the science program with its so-called Earth Explorers, then the European Commission Copernicus program of operational Earth observation satellites that are developed by ESA, and then the operational meteorology missions, which are developed by ESA and then run by ICESat. So these are the three programs. Aeolus is within the science and research program, as well as EarthCare is. So these are both, let's say, first-time technology flying in space. Quick introduction of the specs. So it's been launched, Aeolus been launched in 2018 and summer on a Vega rocket. Main payload is the first Doppler wind lidar in space. Aladdin, operating in the UV at an altitude of 320 kilometers in a dawn-dusk orbit, which has been considered to be optimal in terms of signal return, but also dynamics. Mission control is in southern Germany, ground stations up north in Kiruna and down south in Antarctica, and data processing really distributed among Europe, with an important mentioning of Europe's ECMWF weather center located in the UK, and the data center in Italy, which is doing basically things that need to be close to an NWP model within the ground segment. Mission management at the Earth Observation Center located near Rome in Italy, and the nominal mission lifetime was 3 years, and these have already been reached. So the main objectives of Aeolus are to improve the quality of weather forecasts by providing global measurements of horizontal wind profiles, and to advance the understanding of atmospheric dynamics and climate processes. The long-term goal is to demonstrate basically DWL capability in space for operational use, and as we'll see later on, this has all been achieved quite well. So I'm just needing to move a little bit my control windows here, because otherwise I can't see my own slides. So the line of sight of Aeolus is pointing slightly to the side at a different angle as, let's say, Atlas on EarthCare, or also Calypso, as has been presented before in ICESat. This is simply because we want to see a vertical component of the wind, obviously. It's operating in the UV, and it catches both the Rayleigh backscatter from molecules as well as the Me backscatter from particles with different receiving spectrometers. The vertical resolution is 24 bins that can be programmed, and the smallest bin size is 250 meters in this direction. And in the horizontal, we are looking at between 10 and 100 kilometers, currently differing by the channel being used. And this has something to do with the SNR. Again, trouble with going on here. Yeah, just a quick snapshot of the system when it was still on ground. It's really one of the most sophisticated instruments ever being put into orbit and the first lidar in space from Europe. And it has been developed for more than 20 years. Quick overview slides on the overall status. So basically, we have a set of products on Aeolus, including level 1, which is basically not for scientific use, but the interesting ones are the level 2B, which are the Rayleigh and Me wind profiles for all the vertical bins. Level 2C is basically a superset of model data and to get the full wind vector at the positions of Aeolus measurements after it's been assimilated. And then we have the level 2A spin-off, which is the name for the Aeolus Aerosol Cloud Optical Profile products. So this is, for instance, the backscatter and the extinction, where I always have to say that Aeolus does not have a cross-polar channel, although it is emitting circularly polarized radiation, which means that we are missing out a little bit on strongly depolarizing scenes, but I will say more about that later on. So we do have, obviously, as other missions, also random errors. These are primarily affected by the lower than expected return signals. And we do see some biases, but both of these have been even improved along the mission timeline due to the very strong team on ground that we call the Aeolus Data Innovation and Science Cluster, which is supporting the mission. So this has been established in 2019, featuring several of the let's say, mission experts, which have been contributing to the mission in the decades before, and gathers together experts on algorithms, processors, impact experiments, and campaigns. So these are 14 international partners and currently even more than 40 scientists under the lead of the German Space Office DLR. And it's a DISC managed and it's an ESA funded and managed activity and includes in the regular meetings all the entities of ESA involved. So the control center in Germany, the technical experts in ESTEC and the Earth observation experts in ESRIN, and includes partially even experts from the satellite industry side from Airbus and Leonardo. So now I'll have to read out the slide because I just pasted it in seconds before the presentation because the mission manager told me that I haven't been using the right one. So this is to give an overview where we stand with the exciting mission. So both space and ground segments are performing quite well and ready to support the last year of operations, which is coming up. So in order to have the best performing laser in action, it was decided to swap the lasers. So in the early mission time, we were running on a laser called Laser A. And there was a strong increase of the UV energy with the system, so we switched over to Laser B. Now, the Laser B featured a very high energy, currently even above 100 millijoule. But on the other hand, due to issues probably with laser-induced contamination, there was a strong decrease over time. And so there was a decision to switch back to the FMA. So currently, the FMA laser shows very nice results. Internal signals are around 65% higher than with FMB, although even FMB gave us still at the end a very nice impact in NWP, and we've seen improved random error of 28%. But yeah, the instruments are, even if we get FMA stabilized, not the only limiting factor to the mission lifetime, which is already exceeded by more than a year now. It's also the solar activity because we have low orbit and there's a drag. So looking also at the fuel budget, it is realistic to expect a re-entry sometime next year, most probably in summer. Yeah, so before the laser switch, we did see a major release of updated processors. Currently, they're being tuned towards the other laser, and then we will see another final release of major processor and scientific product updates next spring. The rest of the updates will then already fall into phase F after the deorbiting of the satellite. One nice other thing to mention here is the release of an early mission low bias data set, which is newly available, and I think can be downloaded probably already next week. For the science, I have a gathered a few examples. This is only an overview slide of 6 projects that came out of a tender from last year in order to find potentially new products, as was done, for instance, on Calypso fuels into the mission, which are way beyond, let's say, the current standard mission products, looking at returns from the ocean, additional ways to improve the aerosol products, and so on. And 2023 would be the year where potentially these projects could then lead to actually one or the other project and product being picked up in an operational frame. So we're looking forward to that. And then having again a look at the science, at the main science objectives. So we currently have 7 weather centers operationally assimilating the wind products, which is obviously a sign that our main objective is met quite well. The impact is particularly strong in the southern hemisphere, the tropics, and then especially in the coming from the UTLS region. And one thing is that the 48-hour forecast in the tropics of the upper troposphere, I think, is the strongest that we see overall. On the right side here, basically indicated in this image, I don't know if you can see my mouse, blue, and especially the check boxes means good. Going on to the next, from the several events and science activities in which we were able to track aerosols, clouds, or dynamic winds originating, for instance, from volcanic eruptions or wildfires. I just selected this one slide for today, showing how we were able to track from the first day the plume of the Hunga Tonga Hunga Hapa volcano eruption. And then we quickly actually updated the programming of our vertical range bins to reach even above the 28 kilometers, I think, that were set before, in order to really fully track this event, because we thought that the plume was, in the beginning at least, reaching even above. And the plume in the end may be a combination of aerosols and clouds originating from the water vapor that was injected into the stratosphere. And we were seeing that over months and months. So we still maintained these special range bin settings in tracking the plume until the very end, when we switched on the FMA laser a couple of weeks ago. This slide is a little hard to read, and I cannot go through the whole of it, but I put it in here because it's basically one of the newest disk childs, which is coming out of a science project in which we are actually starting to assimilate the Aeolus Level 2A backscatter products into the atmospheric monitoring, the atmospheric composition model camps at ECMWF. This is currently not done at the operational branch, but it is done, let's say, without any current effect on the model, but it is giving us already a nice indication of, let's say, how the impact could look, but it is also expected to be a nice tool for control of the data quality of these products, not only the wind products. Calval for Aeolus is a large team effort, so one powerful tool is obviously the NWP monitoring done at the different weather centers, but we have more than 30 teams selected via a permanently open announcement of opportunity call with co-located measurements from other satellites, and modeling and science activities, ground-based measurements, and a number of partially really large measurement campaigns on ground, which we benefit a lot from. And on the second slide, just if we have a look at what comes out of these measurements as a synthesis every half year, when all the individual reports are being synthesized by the disk. For instance, we get these nice time series of where we stand in terms of random errors and biases. If we look at the different measurements of the references. With this, I go to having a look where we stand currently in the overall expected timeline of the mission. So we are currently in late 2022, where the reprocessing of the FMA is becoming available. heading towards an end-of-life activity workshop, which is held ESA internally with some invited experts in order to determine nice and interesting, let's say, experiments that can be done with the instrument in the last half of the year. Then we are looking at another release of a major processing baseline, as already mentioned, and number of topical meetings coming up next year for gathering the community, and also one major workshop planned for May. And this will then be followed at some point by the re-entry of the system, and what we then in ESA called the transition to the so-called phase F. But that's not all. Looking at what is coming next, obviously, Aeolus is a technical demonstrator, and we are hoping for an operational follow-on, which are currently in the early development stages at ESA, and the potential operator of the satellite, which would be EUMETSAT, because it's a meteorological satellite. All is looking quite good at the moment. Lifetime of this system would be longer than Aeolus. It would be 2 consecutive satellite concepts in order to reach an overall duration spanning more than 10 years. And it would be a bistatic configuration, which is more atlas-like, because this does remove a few single points of failures for Aeolus. And it's safer in terms of laser-induced contamination, damage management, gives more redundancy, etc. But it's also a heavier system. This is the idea here. But even before that, we will see EarthCare launched, currently planned for 2024. This system, it's ESA's mission for, let's say, radiation, clouds, and aerosols, and brings together on a platform which is the biggest one on an Earth Explorer so far, a JAXA-provided cloud profiling Doppler capability radar, high performance, high spectral resolution UV lidar provided by ESA, along with a multispectral imager and a broadband radiometer. Since ICESat uses a lidar, I'm also just looking here a little bit more into the aspects of the lidar. So again, it's in the UV, linearly polarized, pointing 3 degrees off the nadir to not get the direct, let's say, feedback from oriented particles in ice clouds. UV, why? Reason here again is the higher return signal from the backscatter. And it will allow aerosol typing. So in addition to Aeolus, it does also feature a cross-polar channel, which we might also see on the Aeolus follow-on. And the resolution is much higher. So long track, we're looking here at 285 meters with 2 shots integrated. The vertical resolution also higher at 100 meters minimum to 500 meters maximum. Looking at the number of products from EarthCare, these are much larger than on Aeolus, obviously, due to the combination of the different instruments and the large number of synergy products using different data streams. On the left side here, vertically integrated products. On the right side, profile products. So quite impressive. And I picked this nice slide from a colleague just to give an overview of these type of profile measurements in terms of data record continuity. So coming from missions like even ICESat, currently Aeolus, Calypso, CloudSat. So in red, basically the aerosol measurements, in blue, cloud and precipitation, and in yellow, radiation. Then moving on to EarthCare, and then hopefully later on to missions like AOS, Aeolus 2, and on the radiation side, Libra, and whatever will come next, hopefully, to give us a, let's say, more or less gapless time series of these important profile products. I shall come to my summary and conclusion now. First European LiDAR and first wind LiDAR in space and operations now for more than 5 years. Lifetime objective exceeded. Basically, all the mission objectives met. Positive impact for NWP with several weather centers assimilating. demonstrating wind lidar technology, including the operation of a laser in UV. This was achieved too. HSL approach in space, paving the way for follow-ons like EarthCare and Aeolus 2. To mention again that it was basically an essential contributor to the success to have the Data Innovation and Science Cluster supporting ESA with the mission. And now the community and the team are looking forward to the additional lifetime of Aeolus. And of course, also the years of exploitation that we're looking forward in Phase F with further reprocessings and exciting updates of the mission products to come. I think that is all I have for today, and I'm saying thank you with an image from our last workshop, which was held in Sicily.
Wonderful, Jonas. Congratulations on such a great mission. It's great to see all of the results so far. So next we have Andrea Porter. She's from NASA Goddard. And as I mentioned at the beginning as well, she's applications coordinator for the Global Precipitation Measurement Mission and the Aerosols Clouds Convection and Precipitation Study. Today, she's also going to focus on the future. So she's going to tell us all about the atmosphere observing system. Thanks, Andrea. If you could do a sound check.
Okay, can you hear me?
Okay, wonderful. Yes.
Awesome. Okay. 1 second. You can still see the main slides. You can see me and hear me now.
Yes. Perfect. Thank you.
Okay. Thank you so much, Sabrina. As Sabrina mentioned, my name's Andrea Portier. I am the applications coordinator for the Atmosphere Observing System, or AOS. And so today I will be giving you an overview of AOS. Again, this is going to be taking a slightly different perspective than the previous talks because AOS is a future NASA mission. It's not expected to launch until the late 2020s or even to the early 2030s. So you may be wondering, why are we focusing on these efforts? As you know, other missions that have these atmospheric lidars will most likely not be operational by that time. So, right now is a good time to make awareness of what types of atmospheric lidars and other missions that have other instrumentation that will be there in the future. But also what I want to kind of talk about and bridge into is, this is the ICESat 2 applications workshop for atmospheric applications. It's expected that ICESat 2 will still be in operations in early 2030s. So how can we start to understand and create awareness of integrating data sets between AOS and ICESat 2 to enhance and even improve applications going forward? But to even do that, I guess you need to know a little bit more about AOS, right? All right, so hopefully, okay, there we go. Just taking a step back, I do think it's important to understand where the science behind AOS comes from. So it really starts off with the 2017 NASA Earth Science Decadal Survey. Part of this survey, it outlined an observing program with multiple mission components to address key science and applications for the coming decade, but also to address gaps in the current observation record. And so to address both those, the current gaps, but also key science and application objectives, they recommended 5 designated observables and deemed them as most important to address those, which are from surface biology and geology, surface deformation and change, mass change, aerosols, clouds, convection, and precipitation. Now, originally, these were floating as separate missions, but the fundamental science links between aerosols, clouds, convection, and precipitation, they combined into one study. And originally it was called the Aerosols, Clouds, Convection, and Precipitation Study, but now it is called the Atmosphere Observing System. And I just want to clarify, we are in pre-phase A, meaning pre-phase architecture. So the architecture is not built yet. And so we're in the very early stages of this mission life cycle. All right, I would be remiss if I didn't include this part of the decadal survey where the decadal survey had a strong applications focus. And so what you see in the image on the screen is taken from the survey's public briefing, where they highlighted the importance of Earth observation for tackling societal needs and addressing societal needs with the use of Earth observation data. And so why I bring that up is while we put thought into the science part and addressing and advancing science moving forward is that putting thought into applications prior to a mission launching can ultimately amplify societal benefit for a NASA mission. And that's where I also want to bring up that part of the applications impact team of AOS, we are charged with ensuring that applications are considered to the greatest extent possible. Okay, so where does AOS build from the decadal survey? While aerosols, clouds, convection, precipitation, observables can address a number of the science questions from the decadal survey, AOS is based on addressing 3 primary questions of understanding more about climate feedback and sensitivity, convective storm formation processes, and aerosols, specifically air pollution processes and distribution. To address those, the AOS science team came up with 8 science objectives to address those questions, which are within the rectangular box that you see on the screen on the right, from anywhere from low and high cloud feedbacks to cold clouds and precipitation, convective storm systems, aerosol redistribution, aerosol attribution, air quality, and even aerosol indirect and direct effects. Now, from those science objectives, a series of geophysical variables were proposed in order to address those science objectives, which in order to address the questions at hand. Those geophysical variables help us understand and to propose an observing system and instruments in order to address those science objectives. And that's kind of where I'm getting with this slide, is that over the ACCP study period and also during this pre-phase A time, over about 100 architectures were proposed and recommended. And now we whittled down to 1 architecture that's recommended, and it's in that stage where we are our HQ headquarters is reviewing that to see if that's the architecture that we will move forward with for AOS. So as I mentioned, the AOS architecture is still pending, so this is not final. And so what I want to do is kind of give an overview of what the current status of this architecture is AOS is proposing to have instrumentation in 2 orbits, a polar orbit and an inclined orbit, both serving 2 different purposes. The polar orbit will be sun synchronous and passes over a given location at the same time every day. And the idea for the polar orbit is to actually address 2 of those fundamental decadal survey questions, climate feedback and sensitivity and aerosol processes. And in order to do that, we really need that global coverage. And that's what the polar orbit is going to provide. And it's going to build on the A-train capability of satellites kind of following after one another. And I'll get into exactly what's in the polar orbit in just a few slides. The inclined orbit is going to be an inclined orbit with about a 55-degree south to north degree latitudes. And that the goal really is to capture that diurnal variability. Incline, we're trying to address convective storm processes. In order to get convective storm processes, you really do need to understand more about the diurnal variability. This will be similar to the Global Precipitation Measurement Mission, or GPM, in a sense, in the inclined orbit. All right, so what I want to do next in these next several slides is I want to kind of take a deeper dive into each of the orbits and the instrumentations on board and how it impacts applications or the proposed applications moving forward. So I'm first starting with the inclined because it's going to, the idea is to be launched prior to the polar orbit in 2028. There will be 2 spacecrafts, one operated by JAXA and one operated by NASA. What JAXA is proposing to provide is a wide Q Doppler radar at nadir. And so what's going to do is build on the GPM-like capabilities. The goal is what you see on the left top of the screen is the dual frequency precipitation radar, an instrument on board GPM, which has the capabilities to measure drop size distribution, precipitation phase, and really look inside the storm. Now, what AOS is proposing to have for this Doppler radar is to have a denser sampling coverage at nadir. And so if you go to the left bottom of the screen, is really to smooth out those upward vertical and downward vertical drafts to really understand the vertical motions going on in the convective system. But on top of that, the idea is to look at phase transitions across the melting layers. So to really see these clear objectives within a convective storm or convective system. Adding to the radar, though, the French Space Agency is going to provide 2 microwave radiometers. One will fly with JAXA, one will fly with NASA. These microwave radiometers will be able, with the frequencies on board, will measure brightness temperatures to discern between ice cloud properties. But the fact that one's going to go on one spacecraft and the other on the other, we'll look at the change of rate between brightness temperatures, which will give us a lot more information about the convective vertical ice mass flux. And so combined with the Doppler radar of looking at vertical motion, it can tell us a lot more about these mesoscale convective systems and developments in precipitation systems. What NASA is proposing to offer is a backscatter lidar with 2 wavelengths. And so it's going to be similar or even better than Calypso. It will be able to provide information about aerosols, clouds, as well as the boundary height layer. And so taking a step back by understanding more about, let's say, aerosols, clouds, cloud top heights, and really the vertical motion, we can get a sense really of the storm and the diurnal variability of aerosols and clouds throughout the day, which, as you know from the past presentations, it can have a lot of implications for air quality forecasting, smoke plume transport to weather and climate modeling. And that's what I want to talk about in the next slide, is really breaking down some of those the instrumentation and the impacts towards societal applications. As I mentioned, for the backscatter lidar, it'll give us a lot more information about cloud and aerosol properties, but it will also be able to give us more information about aerosol type and plume heights in the vertical profiles of aerosols. With that, and on a diurnal capability, is that it could help us improve air quality forecasting. As I mentioned, the vertical profiles could help improve the tracking of smoke transport. But also with tracking the vertical profiles, we can help support hazard warnings for volcanic ash and sulfate discrimination and plume height. For the Doppler radar, as I mentioned, really the idea is to discern between the vertical motion and really dive deep into a convective process. And so by understanding that and capturing it over a diurnal cycle, it can really help us improve parameterizations of models and model performance for improved weather forecasting. And that's one thing that I wanted to highlight. So I'm really working, what I'm trying to kind of skim over for this PowerPoint slide is working from the first column and the last column to the right. Last but not least, as I mentioned, with the radiometers paired with the radar, it can give us a lot more context for vertically resolved observations from the radar and really take a deeper dive into what's going on in this in a mesoscale convective system. Okay, so now onto polar, the polar orbit. It's proposed to launch in around 2030 or so. The goal is that NASA providing a lot of instrumentation, but also the Canadian Space Agency will provide some of the spacecraft instrumentation. What NASA is providing to offer is a W and Ka band Doppler radar. It will have similar capabilities to what's proposed on the incline. However, with the W and Ka band, it will target more of your mid to high latitudes because of the polar, but also target more of your weaker convection systems. And capturing all the types of convective systems and all the precipitation systems globally is really important to looking at weather and climate scale processes. For the microwave radiometers that are proposing are going to be similar frequencies, again, like the incline, but also with a little bit of higher frequencies to really capture some of those high top cloud or cloud top height properties. Again, more information from brightness. More information about gathering information about brightness temperatures can have us more information about convective systems. What also is proposed for the polar is a high spectral resolution LiDAR at 532 wavelength. And I feel this group is fairly familiar with the idea that the potential to capture aerosol and cloud backscatter coefficients and also aerosol cloud extinction coefficients. Paired that with the polarimeter that's exposed, proposed for this, is that it can give us a lot more information and constrain about aerosol retrievals. And then on top of that, the polarimeter can provide information about cloud top properties. The Canadian Space Agency will provide a radiometer and a moisture limb sounder with the goal to provide information on aerosol extinction profiles, water vapor profiles throughout the troposphere and stratosphere. So I'm going to do the same thing, what I did for the inclined is, what does that mean in terms of societal applications? With the HSRL lidar, discerning between cloud properties, aerosol types, and vertical profiles, we'll be able to understand a lot more about how these systems and to improve air quality forecasting and numerical weather prediction models. Again, vertical profiles can help us improve tracking of smoke transport and looking at aerosol type discrimination between ash and sulfate that are critical to support hazard warnings. For polarimeter, as I mentioned before, paired with a lidar, it can really help us constrain aerosol retrievals. And the idea behind this is that it will provide a larger swath and a wider context for the lidar footprint that can have us enable more information about extinction and aerosol emissions, as well as long-range transport. Okay, for the Doppler radars that are proposed, again, we will be capturing items, information in the vertical, but at a weaker convection, but on a global scale. This can have critical information and importance for improving observations for numerical weather prediction and climate modeling, because again, the polar orbit is going to have this global coverage. Last but not least, the radiometer. As I mentioned, it will have similar frequencies like the radiometers on the incline, but also have some higher frequencies. With the higher frequency microwave channels, along with the program of records, such as, let's say, hopefully GPM still around, it can help us support the development of level 3, such as graded precipitation products, and level 4 products that can be used not only for numerical weather prediction, but also for a range of hydrometeorological applications. All right. So I know I threw a lot at you, but I really just wanted to give you a big overview of where AOS is going, and the idea of where some of this architecture could help and enhance applications moving forward, let's say after Calypso is not operational. I do want to take a step back because I think I really honed in on a lot of for smoke forecasting, air quality forecasting, weather and climate modeling. But AOS's goal is to tap into a range of applications. And so by taking all these instruments together, it really can tap into other applications such as energy, transportation and logistics, water resources, and agriculture. And so this is something to recognize as we move forward in the capabilities of AOS. So to wrap up, I just have a few more slides. Is just a reminder is that part of the applications is that we are starting now in our engagement efforts because we want to make sure that we are ensuring that applications are considered to the greatest extent possible. So that means we're engaging communities now to learn about their latency needs, user needs, identify proxy data. So at the time that AOS launches, stakeholders are ready to use AOS data. As part of our deliverables for AOS as the applications team is a project applications plan, which part of this plan is to help define what our early adopter engagement and activities are. And a lot of this is we can learn from previous mission successes such as ICESat 2. So in summary, AOS science really does flow directly from the NASA Decadal Survey. So the recommendations that are proposed to address the key science and applications for the coming decade. Again, as we are in the early stages of AOS, we're in pre-phase A. The architecture is still contingent on headquarter reviews, decision, and funding. That being said, if there's changes in the architecture, it could possibly impact the types of applications that AOS can address. But I think that just means how important it is to talk to the community of what's needed in the future to address many of these applications going forward and to enhance and improve them going forward. So again, I said that applications team is actively involved now with communities. If you want to become involved, you're welcome to reach out to me. Even though we have a long ways to go before the actual launch of AOS, we want to hear your feedback. We want to hear all from you. So again, please don't hesitate to reach out to me. And with that, I'm going to stop and pass it back over to Sabrina.
All right, thank you so much, Andrea. And so this takes us now to our discussion session. And I'm going to invite both Stephen and Jason to join me here. I'm going to share a couple of questions that we have prepared for this open discussion. And so the goal is really to learn about your requirements for the data, the needs that you have. And I'm looking at the list of participants, and I noticed we have representatives from Louisiana State, the Department of Transportation, from the U.S. Forest Service, from NOAA. So I would love for you to provide feedback on this question. So first, Jason, would you like to say a few words and lead us into the discussion?
Sure, thank you. No, I think you've outlined some great discussion topics here. I'm excited to hear from the participants about what sort of opportunities they see with what they've heard today and in the future.
Perfect. And I don't see Steve here. Let's see. Yes.
I'll also keep an eye on the Q&A as well as we're in this discussion session.
Yes, perfect. And yes, so if you have any questions at this point, I would ask you to raise your hand so that we can unmute you, so you can voice those questions. There was one from Omar earlier on, and so Ute or Steve, maybe if you could help us with that question from Omar, and let me just pull it up here. Let's see. And if you see it first, Jason, because
Sure thing. Let's see here. So Omar asked if, I believe Steve was speaking at the time, if Steve could say something about the assumed lidar ratio for the ICESat retrievals. Does ICESat use a generic value for all aerosol types, or does it type dependent?
Okay, so ICESat actually.
Hold on, I can answer that.
Go ahead.
I'm here. I'm here. I just couldn't find the unmute button. Okay. Yeah, it could have been a little confusing from my talk because, I didn't say explicitly that we didn't have layer optical depth, and that is where you really need that extinction to backscatter ratio and where that would come into play. That is, like I said, for future development, that's what we want to eventually put in there for the next version of the version following that one. But what we do have is column optical depth, and that is independent of any type of extinction to backscatter ratio because it's just using the what I call the ASR, which is apparent surface reflectivity, which is the ratio of the received energy to the transmitted energy. And from that, and a knowledge of the true surface reflectivity, you can get back the column optical depth. So you don't have to involve the backscatter at all or a backscatter to extinction ratio. But as we go forward, we're going to need to address that problem, because different aerosol types, different cloud phases, mixed ice phase, water phase, they all have different extinction to backscatter to extinction ratios, and we'll have to develop methodology. And one of the good things is, because of all the work Calypso's done, we have a guide, if you will, that can help us. Hopefully that answers the question.
Yeah, that sounds good.
Okay.
It makes sense to me. So I'm curious, questions out there. Does anybody in the audience like to talk about what sort of, we can talk about the, one question that's the hardest to address is how does latency of data products of these ICESat 2 data and LiDAR data, for instance, how does that impact your application? Like what are your latency needs? Is there anybody out there in the audience who'd like to comment? Or another way to look at it, I see right here in the question, is the needs of data continuity, or the question of data continuity. I kind of had the suspicion with Calypso, the eagerness to to assimilate Calypso data operationally was kind of like hindered because it's a research mission. How long is this going to last? Um, so I'm really pleased with the discussions today about, especially with AOS going forward, of getting early adopters on board ahead of time, so that way people can start building up the resources and the infrastructure for something, so that there can be really good use of something in the future.
This is Lauren Zamora. I'm a researcher at University of Maryland, and I've spoken a little bit with Steve before, but this is kind of regarding Jason's question and also more generally. In the past, things that I have wanted to use ICESat 2 for was to look at the Hungatonga volcano, and then also we have an upcoming aircraft campaign which is going to be in 2024. And so it's not really clear whether the Calypso data will be available. And I don't know whether EarthCare will be up. Maybe it will be. Maybe there's more information on that. But anyways, ICESat 2 would be one way to get information on the on aerosols during that campaign, but the latency issue is a problem. And in particular, what I would think would be valuable, if it's possible to do, would be to get more information on the folding, because if you have clouds at a certain altitude or aerosols, for Hungatonga, the aerosols were quite high. And then it was difficult to say what altitude they were since they were folded in. So if there could just be like on the quick look product some flag for whether the data were folded or not, since it takes so long to get the final data available. Just those quick look products, that would be really helpful. Thanks.
Okay, it was Lauren, right? Yeah, Lauren, thanks for those comments. Yeah, one of the problems, of course, is the folding. But when you're talking about things like, volcanic eruptions that send plumes up to 30 kilometers or so, you get this folding down. I can give you an example. If you have a plume at 25 kilometers, let's say, right, where that would show up in our ICESat-2 data would be 25 minus 15 or 10. But the problem is you don't know, like you said, you don't know whether that backscatter, that feature that you're looking at 10 kilometers, you don't know whether it was really there at 10 kilometers or whether it was really at 25, unless you have some other, ancillary data that can, that can give you, tell you something. If you're going over, the known area of the plume, let's say from, the UV or the limb sounder satellites that told you, yeah, it was in this area, then, you can probably rightly assume that, yeah, what I'm looking at 10 kilometers is really that plume. But yeah, it is a real a real bummer, to put it, that we have this limitation, and it's due to the high repetition rate of the laser. That, the pulse prior to the one you're looking at is where you get that folding effect from, because the pulses at 10 kilohertz are only separated by 30 kilometers. And so that's where you get that, 15 kilometer folding thing from. But, I also wanted to say about the data latency. Jason was really, really good, talking about all the applications of Calypso and how just, what was it, Jason, maybe a couple, was it a half a day or a day latency?
Right, half a day to a day.
Yeah, even that latency is really too much for a lot of applications. And of course, ICESat-2 is at 3. And, I don't know if maybe something to look into is, can we reduce that latency to get it down to something more like Calypso? But yeah, it's both the latency and the folding is a problem. But yeah, I guess for the quick looks, like you said, Lauren, I could put maybe something on there, but it really would be limited to cloud folding because, like I say, there's no way to tell whether you've had something from the stratosphere folded back down without some type of ancillary data. And of course, these are produced, as soon as we get the data. So
yeah, if you could have faster latency and of course the whatever folding data that were available, I think that would be really helpful.
yeah.
Lauren, what sort of latency are you looking for?
Well, for an aircraft campaign, the sooner the better. I don't know exactly. I'd have to think about it a little bit. Probably we'd have to be looking at the campaign would be in the Arctic, and so we'd have to be looking at subarctic data, and then using a forecast model to kind of move it to see where it might be going. That's probably the most. I don't know. I guess I'd have to think about it a little bit more, but either way, the sooner the better, I guess. If you want, I can get back to you on that. I need to think about it.
Yeah, no, of course. This is just the start of the conversation, so it's great information.
Well, one good thing is that if your mission is going to be in the Arctic, like you said, you shouldn't have much of a problem with folding because really that's limited, to the tropical regions as far as clouds go. But if you had PSCs or volcanic eruption, that could be a problem. But in general, when you're in the Arctic, outside of the tropical region, folding isn't a problem.
Great. Thanks.
Yeah.
Yeah, it'd be exciting to see what you learn from that campaign. Hunga Tonga has been a pretty remarkable event.
Yeah.
All right, and I should mention that Lauren did let us know that she had a comment via the chat or the Q&A. So feel free to do that, and you can also raise your hand if you want to comment on any of the questions. We talked about the different missions, Calypso, all of the applications there, and AOLIS, and then thinking into the future with AOS. Is there any other improvements, or I guess gaps in the data that is being collected so far? That would need to be addressed by this future mission?
Anybody in the audience like to take that?
Everybody is very quiet. picking on people then.
I mean, one thing we always point out is that there is a pole hole. So I see AOS will have a polar and an inclined component. So we should definitely cover the entire globe. Now for ICESat-2, it's a pretty small hole, but it's still a hole. Then, of course, if we can develop sensors with better spatial coverage, that would be good as well, although the atmospheric features tend to be kind of large anyways. So I think you don't miss as much, right? And of course, what makes data fusion difficult is pretty much the opposite of what I requested just in the last two sentences. Namely, if the missions would fly all on similar or the same orbits, then we would have an easy time integrating or comparing the data, while now we're sort of stuck with certain crossovers or saying, well, this feature covers 1,500 kilometers, so it's probably going to show up in more than one satellite. Right.
And that'll be kind of
definitely
part of the.
Yeah.
Oh, I'm sorry. I was going to say that's kind of the benefit. The multiple instruments in the AOS constellation, they're going to be co-located by by the design.
Mm-hmm.
And that'll certainly help. And you're right about the different orbits are really helpful because the being able to capture the diurnal variability is huge because, for instance, wildfires are most active in the late afternoon, whereas right now, like Calypso, for instance, is only sampling in the early afternoon, so it never really sees the real biggest fires, whereas that inclined orbit will give that nice opportunity to sample that.
Yeah, so the only disadvantage with that is it's another 10 years until we will have all this data. So
Fair
in
enough.
the meantime, I told my students to get on because, I mean, realistically, right? It's going to be another generation, perhaps, had by us, but looking at the data. So far, what can we do fusing the data that we do have? Solving challenges of today, right? We can't just sort of let it go for the next 10 years saying, yeah, we'll be able to look at stuff then.
Right. A lot's going to happen in the next 10 years.
Right, and with that regard, Ute and Steve, we've talked a lot about sort of the potential for applications for ICESat 2, and just based on the feedback that we got from Jason and all of the great applications from Calypso, what do you see as a possibility based on the capability that ICESat 2 has for those types of applications as well? This could be a question for all of my speakers here.
Well,
Yeah,
I have to say I was like plain impressed by the breadth of applications that Calypso has. I was gonna just say, hey Sabrina, there are a list of 30 applications which I haven't thought of personally. Of course, Calypso is a dedicated sensor for atmosphere, but hey, there are so many ideas. And of course, it's been around for 20 years, right? But what similar types could be solved with ISA 2? Yes, Steve.
Yeah, I agree, Uta, and I really would like to sit with or spend some time with Jason to go over each one of those things. I wrote them down, and of course, having his presentation will help. But all these different areas that Calypso is now, providing data for, I think what we need to do is identify which areas ICESat 2 can step in for Calypso, when Calypso goes to heaven, shall we say, at the end of next year. And, like the air quality and smoke plume height, the aviation safety, et cetera. I think, whatever Calypso is doing there, I think we can have ICESat do as well. So I think we really need to go through the list, Jason, and see if we can actually identify the different areas that we might be able to be useful.
Yeah, that's a great idea. And there's a lot of places where ICESat 2, could work equally as well. I know if I'm using clouds to validate retrievals and whatnot, ICESat 2 captures a number of clouds in the mid-troposphere. It could really be beneficial
Right.
for that.
Right.
So definitely opportunity.
Mm-hmm.
And Lauren, you're unmuted now. You had a
Okay. Sorry. This is I was actually just trying to put my hand down, but since I'm unmuted, I also was just thinking, the lower I mean this is kind of obvious already, but the lower data quality during daytime is definitely a problem for polar applications during the summer. So just putting that out there. I don't actually have suggestions for you to address that. I just and I'm sure you're already aware of that, but that's one challenge for people wanting to use the data.
Yeah, well, it depends on if you're talking about, aerosol detection.
Yeah.
Okay, yeah, that is a little problematic. Of course, the normal approach is, averaging the data to beat down the noise. So you would, wind up getting, let's say, some aerosol retrievals, but at lower resolution. But I wanted to say that the DDA that UTA has developed is remarkable in how well it can pull out things from the noise. And, she might even be able to improve upon what we already have. But, we still get, even in the noisy data sets, we still get, the cloud retrievals. And, if the aerosol is relatively thick, we get those as well, too. But yeah, you'd really have to go to data averaging, Lauren, to help to beat down the noise if you're looking for aerosol.
Is that available in the version 5 or upcoming version 6 products?
Well, no, it's not. I mean, the data are presented in those products at full resolution. So that would, that would be something, at least at the present, that you would have to do, yourself
Okay.
using the high resolution data. But, that leads to a question. Maybe we need to do some of that averaging to pull out some of the features in daytime and have that on the product. But currently, it's not there.
Yeah, if it were there, that would make users' lives a lot easier, like make it a lot easier to use the data.
Right.
Well, so the thing is, Lauren, first, actually, the Saharan dust problem we have solved now, so that's gonna be available on release 6 whenever that is public, right? So we're looking at the test results right now. There are physical and engineering constraints, so you can only get a stronger signal from using more energy. However, only so much energy can fly on a single satellite. So by increasing the resolution on ICESat 2, you go from the type of sensor that we had on glass on ICESat, right, 30 years ago, 20 years ago, and that's a stronger sensor. Then you have SAR sensors, which go through all the polar clouds, but they measure different things. So technologically, you are only able to pick, you have to make decisions. Either you have high resolution, or you have many beams, or you have a high rep rate, but you can't sort of have both, because you can't fly a power plant. We do have solar panels, which give some energy back, but as you heard about Calypso, the main constraint after 20 years is not that the sensor failed, but the energy goes down. So now if there is another SpaceX satellite crashing into Calypso, it can do one more avoidance maneuver and then it's gone. Okay, so then, no, seriously, that's what I learned at the Calypso Science team meeting. So then, mathematically, detection of all these different aerosol types is actually a different math problem. So we're happy to go to the ICESat 2 project and say, hey, the community wants us to find really thin, really widespread signals, say, over the poles, and I'll see what I can do. And since you say they're lost, would you go and find me a bunch of examples where you think they should be in the data, and I see whether they actually are?
Yeah, maybe that could be done.
Yeah.
If this were, I mean, I don't know if I don't want to speak for the whole community, of course. So maybe there's other priorities, but if you have the time, that might be helpful. Yeah, thanks.
So Lauren, what's the name of the project that you guys are doing next year, you said?
Oh, it's in 2024. It's ARC 6.
ARC 6. Okay. Yeah. I think
Yeah, I just
was
want to
there another
comment that.
component?
Oh, go ahead.
Yeah, there was another component of that, right? ARC 6.
I'm sorry, what?
Hasn't that already been going on, or is this something new?
No, maybe you're thinking of ArcTAS or above, but no, this is a new one focused on like
Okay.
clouds and their impacts on sea ice. But there's an aerosol component too.
Okay.
And Jason, you also had a comment?
Oh yeah, I was just going to comment. So Calypso also struggles with identifying aerosol over the Arctic in the daytime. Similar issue, it's really optically thin aerosol and lots of noise. One thing we've done to help out with that, we actually developed a product called a level 1.5 product for aerosol assimilation purposes, where we took just the normal, basically layer detection, and then filtered out all the clouds from the level 1 backscatter, and then re-average it to a coarser resolution. The idea being is that you have this now a smaller product size for aerosol assimilation, so they don't need all this data. They need something kind of coarse. But what we did over the Arctic experimentally is we, again, just removed all the clouds out of the way because that's noise. We're interested in the aerosol. But then we averaged even coarser, like what Steve was saying. So a product like that might be helpful, like a cloud cleared level 1 backscatter product that you could take and average up even further to try to dig out some of the fainter aerosol. Might be helpful.
Yep, that's a good point, Jason. I think that's exactly what you'd have to do. So,
Well, no, you can aggregate. You don't need to degrade resolution by averaging, I think. Right. But we have this discussion.
Nice.
Yes.
So,
It does not like averaging.
no, because we lose resolution. But I mean, aggregation satisfies a similar purpose. It keeps the resolution by washing the data out ever so much.
Jonas, you have a comment?
Yeah, I just had a general comment because obviously it's looking at the Aeolus, we also had a situation where we had a lower than expected return signal, which means that some of the spin-off products maybe didn't work just as well as we expected in the beginning from the simulations, and which is also why we put a lot of effort in evolving those, borrowing and using synergies from other missions. So we started looking around for what has been developed for AppDet, can that improve the situation? And we then in the end went actually in both lanes. So we went in improving the resolution, going to sub BRC scales, and on the other hand, improving basically the noise by using new methodologies and optimal estimation methods with 2 new algorithms that have been making it into the products last summer. So I just wanted to invite the community in principle to look also what is coming up next, because this is actually the field that we are most active now. The winds are working well, but these are the areas where the most science work is being done and the most progress is being done on the processor developments. And with each baseline, we are still doing quite large steps, and I expect that this will still continue in phase F even for the reprocessings.
Jonas, I had a question for you. Actually, during your presentation, I might have missed it, but my question is, I know that the winds are the main, the main objective for Aeolus. So, but you've got that 355 backscatter profiles. Do you use them for, cloud detection and aerosol detection? And do you have a product? Of cloud heights and aerosol heights?
Yeah, I should have repeated that. So I was referring in the product development exactly to those aerosol and cloud products. So we have products we have backscatter and extinction profiles.
Okay.
With the limitation that we collect only the copolar component of the backscattered light. That means if you have a strongly depolarizing scene, you are missing out a certain component, but this component can normally be modeled. But indeed, these products are used and are even already being assimilated into atmospheric composition models like the CAMS, but not in an operational manner. So it's basically done in an offline version. Yes, this is indeed done, and again, the products are still on the road of improvement. But what we see, for instance, from the latest campaign activities in cooperation with NOAA and NASA in Cape Verde from last September, is that even down to the PBL, the product is quite useful and very close to the high resolution systems that we have been using as a reference on ground.
Will the follow-on Aeolus mission include the copolar channel, or excuse me, the cross-polar channel?
There's a strong push from advisory bodies to consider that.
Oh, excellent.
But it's nothing that I can at this moment say whether it's in the final design, but I know that there's a strong request from parts of the community to have it.
Understood. Thanks. I was going to, there's a question in the chat I wanted to pose before we run out of time. So the question is there any improvement proposed for estimating bathymetry data, specifically river bathymetries for a new mission?
So I can take that because we actually don't have to wait for a new mission. The ICESat science team has a subgroup on bathymetry, which is led by Chris Parrish of Oregon State University. And he actually just gave a presentation at the Oceans meeting, which is published. And so we're actively working on detecting just shallow water. So ICESat can penetrate clear water, as we found, to 80 meters. That's something we didn't expect before launch. So the sensor is doing better than expected. We can find melt ponds on the sea ice, for instance. So I just sent a paper in describing the math of doing that. And Buckley has a whole PhD thesis on measurement of melt-point evolution in the Arctic, combining like Sentinel data and ICESat data. So there is definitely work to come, and you could just stay tuned for perhaps new products being developed in the future. So we don't here need to wait for a new launch.
No, that was one of the biggest, I guess, surprises or really great outcomes of the ICESat mission for bathymetry, right? So Ute, I guess one last question. I know we're at 1:30, but I was wondering, you had mentioned diamond dust as being one of the things that ICESat sort of does. It's one of the only sensors that does it. You know, are there other sort of areas where ICESat is raising the bar over other current satellites?
Well, I really should correct that. I think maybe Uta might have said that ICESat would be the only sensor. What she meant was satellite lidar is really the only sensor that can detect diamond dust because the particles are so small, they're invisible to radar. But Calypso also would have that in their data as well. But I think our group was the first one that was, trying to utilize those measurements to understand, the temporal and spatial frequency and to develop a way to estimate the clear air precipitation that results when diamond dust settles onto the surface. So yeah, so that's, but in terms of, yeah, I mean, where the bar was, I mean, to me, is in the fact that ICESat has this real automatic bore sighting system. And Jason, I don't know if you remember or were part of, but I've known Mark Bone for a long time, and I know that a lot of his gray hair was caused by trying to, calibrate Calypso because of the bore sight changes as you went from thermally induced bore sight changes as you went from, daytime to nighttime. And that one thing that ICESat has now, keeps the bore sight perfectly aligned, and from day to night and in between. And that's a big advance engineering wise. And I can't imagine any LiDAR in the future, satellite LiDAR wouldn't have something like that. But, I mean, there's a lot of, I guess, examples, you could give from altimetry in the photon cloud, to say about, how much higher the bar has been for ICESat. But for the atmosphere, it's kind of a hard one to say because it's not, it's not optimized for atmospheric measurements. But I'll go back to the blowing snow and say that we can detect blowing snow better than anybody.
Great, and we should talk about that in our next session. We're
sorry,
actually we're just going to take a break here
Oh.
because we're at 1:33 and we're due for a 15-minute break. So let's come back at 1:45 for our next session, and we can include some of the questions that we've received as part of the next discussion at that would be at 2:45. So thank you all, and then we come back at 1:30.
All right, thank you.
Thanks.
Wait, do we have? How long is the break?
So we have around 15 minutes, so a little less than 15 minutes now, 1:45 p.m.
Yeah.
US Eastern. Sorry.
That's it, yes. Well, I asked for 15 minutes. I'll see you soon. Time to grab a cup of tea.
All right, everyone. So we are back. It's at 1:45 p.m. U.S. Eastern here. So our next session is going to explore innovative solutions and opportunities to using ICESat data. And we have great speakers on the way. But really, they are going to help us explore sort of that ICESat data potential for various applications. And based on the information that we get from the different missions, help us think about multi-mission solutions towards these applications. So our first speaker is Michael Frum. He's a research meteorologist in the Remote Sensing Division at the Naval Research Laboratory. So I am going to stop sharing my slides here, Michael. If you would like to go ahead and share yours.
All right. Thank you, Sabrina. Let's see how well I can make this work.
You sound great. I can hear you.
Thank you.
Okay, and they're just coming up. Perfect. And if you can put them in
Slideshow mode. Boom. Boom. Okay, how's that?
Yeah, perfect. Take it away.
Thank you so much.
Thanks.
Thanks for the invitation. I'm going to be talking about niche areas of atmospheric science, but I think they are all important. I am from NRL, and I do basic research. I guess I found out this morning from Sabrina's talk that I'm one of those laggards. I'm on the laggard side of that distribution. I've never used ICESat data. I was an ICESat user and collaborator with Steve Palm in the past, and I'll give thanks now to Steve for a couple images that you're going to see pretty soon. So we're going to flip through 3 examples of these niche tropopause level ice, dust, smoke, sulfate type clouds, and how ICESat sees them. Okay, we're going to start with the Pyro-CB, pyrocumulonimbus. This is an animation of a fire that blew up in Alberta in June of 2019. And this is an animation of visible imagery on the top, the 3.9 micron image in the middle showing the fire hotspots, and the window brightness temperature in the bottom. And you can see the visible cloud form, the anvil, and the cold temperatures. This is an active pyro-CBN process, and this was one of the more intense pyro-CBs of the summer of 2019. And as luck would have it, ICESat made a couple strategic overpasses of this cloud. On the next day, in the early morning hours, the cloud was seen in the nighttime VIIRS reflectance channel, thanks to probably a full moon. And the arrow points to the western side of the Pyro-CB blow off. It's about 10 hours old, and you can see the ICESat orbit. And so what I did was I just grabbed the quick look granule, and of course the granule is huge and covers that long latitudinal area, but the arrow points to these very bright elements up north of 60 degrees latitude. That's that little bit of that icy smoke blow off from the Pyro-CB. So that's a very excellent opportunity to observe these peculiar ice smoke mixtures as that plume then flows through the upper troposphere and lower stratosphere. The day after that, the next day, ICESat made another observation. You can see from the map where the orbital swath is, and over Northwest Territories, the arrow points to now a day and a half old smoke plume. So that to me is very exciting, because knowing what ICESat can do in terms of spatial resolution gives us opportunities to look at the cloud top texture and other qualities of these evolving plumes. The next example I'm giving is from a volcano. This is the Raikoki volcano, and this was, it blew up on 22 June, just 5 days after that Pyro-CB. So you had these tropopause level plumes of smoke already in the stratosphere, UTLS, and then Raikoki went off. And this map, again from WorldView, shows the ICESat-2 orbit overlay on the Air's SO2. So that's where the volcanic plume is in terms of that column SO2. And ICESat showed this in that area east of Kamchatka on June 26th, 4 days after the eruption. So again, very exciting. You can actually see a number of aerosol layers below that, but that more intense, long one up at 12 or so kilometers is the uppermost Rykoki plume that was sampled that day by ICESat-2. Okay, the third example is what I call a dust-infused baroclinic storm, DIBS for short. If you are interested in this and would like to learn more afterwards, I put a link to a paper that was written in 2016 where we essentially described the discovery of this peculiar, what they call dusty cirrus cloud. And the importance of these phenomena are that these clouds have a longer lifetime. So we have an aerosol indirect effect in the ice cloud of these dust-infused storms. The clouds themselves have a peculiar cellular texture, which we'll show in a minute, and they manifest a very odd, super intense backscatter. Again, we'll see that in a minute. But first, I'm going to show this animation of this storm that occurred last March. If you look down over Iberia, you see some bright white in this RGB image. The bright white cloud is what we're going to follow. It's starting to get more intense. You can see the cyclonic circulation and then a shield of bright white clouds zooming up over UK, north of Scandinavia, drifting back down over Russia over the span of that 7 or 8 day period. So we were able to track this cloud with GOES imagery, or ICESat in this case, but this is the kind of phenomenon that have intense interest in. These are niche phenomena, but they occur routinely in the winter and springtime over the deserts areas of Europe, Central and Eastern Asia. So because it's a multi-day event, again, ICESat-2 came in very handy with observations. And I just grabbed a few quick looks to show you. The circle, the oval shows you the DIBS cloud from ICESat-2's perspective. And you can just see from the broad array of clouds up in the upper troposphere that it stands out from all the rest. Super intense backscatter, attenuation, total attenuation over a very short vertical range from the cloud top down about 1 kilometer or 2. And this is a classic signature of these DIBS clouds. Highly attenuating icy dust blends. Here's another one. And again, you may not be totally familiar with this, but if you were just to scan through ICESat quick looks or CALIOP quick looks, these stand out like a sore thumb from all other ice clouds. They're synoptic in scale. They have this huge intensity of backscatter, attenuating everything below it. So you might think that this is an opaque cloud. Sure looks like an opaque cloud from this perspective. Here's another one from that very same storm as it moved over the high Arctic. And this is a picture, this is not from that particular DIBS case, but this is a picture over Eastern Europe. Again, this is VIIR's nighttime visible imagery. That is the Black Sea outlined to the east. And you can see the cellular texture of one of these DIBS clouds. Most cirrus clouds in the synoptic scale like this are fibrous and relatively smooth. This structure lasts from the beginning to the end of these storms. And again, I see this and I see ICESat-2 with its great resolution. We could probably make a nice map of the texture of this cloud. And that would be the only instrument that I think that could do that. You also notice that city lights are shining through this cloud. So in that respect, they appear to be translucent. But this very same cloud in the thermal infrared is emitting at brightness temperatures lower than -40 degrees. And so that's a classic opaque cloud signature. So in the infrared, that looks like a classic opaque ice cloud. But in the visible, you can see through it to the lights below. And you can see this in nighttime as well as daytime imagery. I zoomed in on that very image just again to bring out those cellular structures. And if I had really done my homework, I would have gone and measured some of those to give you an idea of how geographically large they are. But I think we calculated in the past that they were maybe 5-7 kilometers in size. But don't hold me to that. But they are small, they're regular, and they encompass the entire cloud top. And that's an important thing to try to understand. It's not just a gee whiz thing. There is a reason for these clouds to be physically and microphysically different, and this could be one indication of how we can get to the bottom of all that. So Steve helped me out with imagery from that March event of this year. This is a triplet of images I'll toggle through real fast. This is from March 16th, 2022, and you can see up close and personal the texture of that cloud from ICESat-2's perspective and the large attenuation. That's the one of the triplets. Here's the middle beam and the other external beam. So, and Steve had pointed out that it's very interesting. The backscatter in the nadir view is more intense than on either side. What that means, we don't know. But I think he found that on a couple other granules that we looked at in preparation for this talk. So again, very exciting. If you look at that particular image, you can actually see those cells individually. And with the triplet, you can actually get a two-dimensional view of that if we were to do some pretty cool mapping of that particular storm. So those are the three niche phenomena that I work on, and want to learn much more about. But while I was thinking about it, there are other phenomena like overshooting thunderstorm cloud tops. If you were lucky to catch an overshooting thunderstorm that was below 14 kilometers, there's an intense interest in cloud top overshooting phenomena and how they appear in visible imagery. They have these things called above anvil cirrus, and I suspect that under good conditions, where ICESat did fly over one of these while that was happening, you would get information in detail that you can't get from any other satellite instrument. So anyway, it's very exciting to me to think about becoming more of less of a laggard and more of a user of the ICESat-2 data. And I again thank you for your time, and just thought I'd present those as some interesting options from my perspective.
That is wonderful. Thank you so much. That is a great presentation. We can take questions here if there are any, or we can wait for the discussion. Are there any questions at this point for our speaker?
So hey, Mike, excellent presentation. It's just so puzzling to me, talking about the dibs, that we can see the city lights below, but yet you cannot penetrate it with lidar.
Right.
And it's just, because I always figured that, from the other perspective, sometimes when you go outside and you have increasing high clouds, right, you see the sun start to disappear, right? So when the cirrus clouds get optically thick enough, you can't see the sun anymore, right?
Right.
And I always thought that was probably about the optical depth limit of a lidar to penetrate through.
Yep.
And that's about in the range of 2 to 4, probably about 3.
Yep.
And so I figured if you could see city lights, which aren't as intense as the sun, right?
Yep.
That you should be able to see a lidar should be able to penetrate that, but yet it won't. So I don't know if it's something unique about these clouds. It's just very interesting to me. So,
well, I totally agree. It's above my pay grade to wrap my head around all this. We've shown the observations. We have asked a lot of people, some people who are much smarter than I am, And I think we're all still trying to figure out just what that means. But for instance, if we think back on that infrared image that I showed you, a classic cloud retrieval from the infrared nadir emitters would have said that that optical depth was probably far exceeding what you might expect for a translucent cloud. So
Yeah.
there are very conflicting signals, but I can tell you that that is typical, that you can see through those opaque clouds, not only at nighttime, but at daytime. We've been able to see these clouds blow over snow-covered ground adjacent to bare ground. And you can actually see the snow cover through the cloud. Otherwise, it would be, I would have thought, impossible to see that with these opaque clouds. So it's a very interesting phenomenon.
Yeah, and one thing you didn't stress anyway is the fact that these clouds have dust in them, and that once the cloud dissipates or sublimates or evaporates, you are left behind with dust. And sometimes you can see that in Calypso or maybe ICESat 2. Is that correct?
That is correct. In fact, there were a couple granules where I could have actually pointed that out or shown that in the talk. In this particular case, you can see what appears to be a fuzzy aerosol layer at the same altitude as the DIBS cloud, north and south of it. So yes, no doubt about it. And I'm glad you brought that up, because that is a critical thing, because indeed the dust is left at those altitudes at a high enough concentration that they can blow completely around the world. They can be detectable with instruments like CALIOP, and I'm sure ICESat too. There was a case in 2010 where one of these storms, several of them, blew up in Asia. The dust blew completely over North America and out to the Atlantic, and there was dust at 10 kilometers altitude at the very same time that the Aya volcano went off. So people with lidars were seeing what they thought was ash, when I could probably show that it probably wasn't ash. It was probably dust that came from a half a world away. So there are real consequences for the evolution of the plumes after the DIBS goes away.
Yeah, and the fact, and you also said, how ICESat 2 is unique in that it has the 3 beams.
Yes.
And we saw the difference between the nadir beam and the 2 off nadir beams, and that's telling you something about particle size or orientation. Like you say, it's probably beyond my pay grade too, but I think that data can be used and interpreted in a way that, well, just one beam isn't going to get you,
Well, I totally agree, and I sure hope that the follow-up to this meeting is an active collaboration and maybe a couple of case studies.
Yep. Okay. Sounds good. Thank you, Mike.
Thanks for that idea, Mike. And yes, so we can have a lot more discussion a little later on. But right now we have Randy Bass joining us from the Federal Aviation Administration. He's manager of the Aviation Weather Division. So thank you, Randy.
Right,
and if you can go ahead and share your slides, or
sure, I can do that.
Sure.
Hold on just a minute.
That has been working well. Perfect. So it's uploading now.
All right, let me know when you can see it, because
Okay.
I can't.
And if we have trouble, I have them ready here for you as well.
Okay, it's can you actually see it?
Nope.
Good, because I can't either.
Okay, let me pull him up on my side then. Let's try that.
Okay.
Okay, so I'm going to go ahead and share the slides and then grant you control. Let's see. And you can accept the control and you should be good to go.
Great, thank you very much. Okay. Again, my name is Randy Bass from the manage the Aviation Weather Division at the FAA. I'm going to go into a little bit of a different direction than most folks have today. I'm going to be talking about our general use of satellite data and some of our research and applications within the FAA to reduce the impact of weather on the national airspace system. But I will talk a little bit about ICESat and Calypso as well here in a little bit later. So first, I'm going to give you a quick update on our description of the Aviation Weather Division. Our goal is to align and manage the weather research portfolio towards new capabilities that reduce the impact of weather on the NAS. Now, we do represent the U.S. as the Met Authority for aviation weather. So we're actually the representatives on the for the U.S. on the ICAO group, and then we assist the National Weather Service on their participation in the WMO for aviation related matters. I'm not going to go through all these, but you can see that basically we're trying to help the decision makers, whether they be pilots, controllers, flight operators, and airport operators, give them better quality weather information, better access to that information, and utilization of that weather information. So it's not just throwing a product over the wall and hoping that somebody uses it. We're there throughout the entire process, and we work very closely with the National Weather Service. Whenever we probably 90% of the new capabilities, accessible capabilities that we come up with in research get transitioned to the National Weather Service for operations. This is just a good slide that shows that we can really utilize satellite data throughout the entire route of flight. Starting with pre-flight as you're preparing as a pilot for looking at things like is there going to be any convection or icing or turbulence in your flight? Obviously winds and precipitation and clouds and pressure. Then once you take off, we use satellite data for cloud classification, lightning, ceiling and visibility, overshooting tops, snow and ice prediction, and then even on landing, the same thing: cloud classifications, lightning, convective initiation, icing and precip, and snow. So honestly, probably 10 years ago, we didn't really use satellite data at all in any of our forecasts or observations, but we've really had a dedicated effort over the last 6 or 8 years to integrate satellite data into our research and into our operations. So one of the capabilities that we've been developing over the last few years is what we call the offshore precipitation capability, which we'll be changing the name of this soon because it has applications beyond offshore. But basically, about 10 years ago, our air traffic controllers down in Miami said, "Hey, we control the entire airspace for the Caribbean, yet we have no weather radar capability there. Can you help us out?" There is no radar capabilities over the oceans. So what we've done is working with MIT Lincoln Lab, we came up with an approach that utilizes any existing weather radar, but lightning data, satellite information, and numerical weather model data, put them through a machine learning convolutional neural network, and basically developed a radar-like product over the oceans that fill in those gaps. And you can see here on the left-hand side, This is what you would normally see with just radar only. And then when you fill in with OPC, you fill in those gaps and show what's really going on out there. And we're just using right now the legacy channels on the goes east, but we have expanded our domain basically from almost the Azores to Hawaii in our experimental site using goes west as well. And we're also looking at using this as a gap filler for the some of the areas in the Rockies where the you're getting some beam blockage from the mountains. We're looking at using this as a gap filler there, and so far the results have been very encouraging. We're working to incorporate satellite imagery into our icing products, specifically the current icing product, which is the icing analysis. This is available on the Aviation Weather Center website to improve the detection of potential icing locations. Right now, we are just using it in the analysis, but the plans are to when we're working with the Global Systems Lab folks out in Boulder to see if there's a way that for the modeling part and the forecast part that we can also continue using the satellite data as one of the inputs. We've also integrated satellite imagery and geostationary lightning mapper data into our turbulence products for specifically our graphical turbulence guidance nowcast. That provides a 0-hour analysis and a 15-minute forecast out to 1 hour. And you can see the difference in between just using a GTGN without lightning, and when you incorporate lightning, you see all the added areas of eddy dissipation rate that's there, and this has been a big hit with the airlines over the last couple of years once we did that. For cloud ceiling and visibility, obviously cloud base height and cloud top height are really important to us on the aviation side. But we're also looking at things like cloud-based pressures, cloud top pressures, VIL, cloud phase, and especially using it as a cloud mask. We're using the GOES fog and low stratus products, looking at seeing if we can use this especially for the San Francisco low stratus issue that occurs in the spring and summer, just basically every year. Really impacts the amount of flights you can get in and out in the mornings, just because their two runways are side by side, and typically runways need to be about 700 feet apart so that you can do parallel operations, but theirs are less than that. So you have to do you can do parallel ops when it's VFR conditions, but under stratus conditions that really limits them, and they can't do that. So it's really important to determine when it starts and when that stratus dissipates. And then we're also looking at filling in some of those observation gaps in the LAMP program. LAMP was originally developed just for taking ASOS and AWOS observations and developing a gridded product from that, but we quickly saw that there's still a lot of gaps in that coverage, and satellite data is helping to fill in those gaps. A couple areas we don't do any research in right now, but are planning to, is space weather. We recently hired a space weather expert to look into especially radiation doses and avionic damage due to radiation. And so that's just getting started. And although we don't really do anything in volcanic ash, obviously you've heard a couple of instances today where ICESat 2 is used for volcanic ash, and I think that's a great thing, because We do work with the Weather Service at this, and we're actually going to start a research project on the volcanic ash and some of the other emissions from volcanoes that impact aviation here in the this coming year. So this slide just shows the currently, if you take a look at here and you look kind of at this horizon, generally from there up to flight 60,000 feet or so, that's where we've always traditionally done our research. That's where the general aviation folks generally fly. That's where the airlines fly, and we haven't done much beyond that. But with the explosion in the commercial space arena and obviously in the UAS arena, we've got to do both the that surface to 3,000 to 5,000 feet, especially the planetary boundary layer for UAS operations, and then above 60,000 feet, really in the stratospheric regions. We're going to be expanding our research into both those areas for all the activity that we're starting to see in those regions. And satellite information is going to be really important for that, because we don't have a lot of other observations in those areas. And so I think that's where our growth area is really going to be here in the future. So use of other satellite data. I think both ICESat-2 and Calypso could potentially be used in our work as validation sets. The data latency, whether it's 12 hours or 3 days or whatever the case may be, really doesn't work for operational uses. But I really see it as we could use these validation sets, because we really struggle with even when you're talking about cloud heights and cloud top heights and things like that. We still have no good ground truth for that kind of work. So and like I say here, cloud analysis and forecasting is really a weak area for us. And we're barely scratching the surface on using satellite data. We're getting better at using GOES data, but some of these other missions I think we can utilize in the future, at least in research. In summary, the Aviation Weather Division conducts applied research to minimize the impact of weather on the NAS. There's been no commercial airline accidents, at least fatalities, fatal aircraft accidents due to weather in almost 15 years now. We've really cracked down and done a great job on the commercial side. But that doesn't mean that we can just sit back and go, that problem is solved, because once we let our guard down, something bad can happen. But weather's still the leading cause of accidents, especially fatal accidents on the general aviation side. Unintentional flight into terrain, mostly because of VFR pilots flying into cloud cover that they weren't expecting, is still a big issue, and that's something that satellite data can obviously help with. And we're leading significant research to exploit and integrate that weather satellite data into our products and capabilities. And again, we're open to using ICESat-2 data as a verification and validation data set. And with that, I'll stop there. And if there's time for questions, I'll take them. And if not, later on, I'll still be here to answer questions.
Okay, great. Yes, I think we do have. Let's take one question and then leave the rest for our discussion session. I saw one coming from Dave Jones. So, Randy, does the FAA have a test bed for trying out potential products and working with other agencies to leverage their data sets or data assets? I'm sorry.
Sure. Hi, Dave. Yes and no. Do we have a dedicated test bed? Yes, up at the Tech Center in Atlantic City, we do. But that's really for testing sensors and things, especially ground-based sensors. As far as new products and things like that, we do have a test and evaluation team that will go out and work with potential users to test new capabilities and products to make sure that they're they do as intended and are used as intended. And we also work with the NOAA folks who do a lot of our third party independent evaluations, quality assessments of those products. But as far as a true test bed, most of the time, our new products get tested with during the Aviation Weather Center's summer and winter experiments, and we do it that way. So and work with them as our other agency. We are looking to expand, and it's one of the things I've really been pushing the last couple of years is working with other agencies. We work with NASA some, but we're starting to work with even DOE and some of the other groups to leverage what they're doing that may have aviation applications, and we're certainly willing to provide our work to others that because we know that the stuff that we do for aviation has applications beyond that. So we really are looking at some cross-agency collaborations.
Great. Thank you so much, Randy. And so we'll take any other questions during our discussion session. So next up, we have Zheng Liu from the Applied Physics Laboratory at the University of Washington, and he's going to tell us all about the relationship between the Arctic sea ice leads and cloudiness in cold months.
Let's see if I can share. So can you see this?
You're good to go. Yep. Thank you.
Okay. So my name is Zheng Liu. I'm from University of Washington, and I'm going to present today our work on the sea ice leads and the cloudiness in the Arctic region in cold months. And this work is supported by NASA interdisciplinary research. I also want to acknowledge our collaborators, Ron Kwok and Steve Palm, for their help and advice on ICESat datasets as well as the project overall. So first of all, the motivation. We know that leads are just cracks or channels of open water in sea ice. Their spatial coverage in the Arctic is usually small, 1 to 2% in the wintertime, but they can account to up to 70% of the total heat flux from the surface to the atmosphere. In addition, cloud plumes can form directly from leads and reach up to 4 kilometers height and tens of kilometers downwind. Over the years, there have been a number of studies using models to examine the relationship between cloud plume formation and lead characteristic, and they all suggest that the open leads will tend to increase cloud cover in the Arctic region, and this is important because it will feed back to the surface energy budget and affect sea ice growth in the wintertime. But on the other hand, there are also potential mechanisms for leads to decrease cloud cover. In a 1978 paper, it has shown that as soon as the leads begins to freeze up, the heat fluxes decrease very rapidly. More recent studies by Lee et al. Have shown that even 5 centimeters thick of new ice is enough to cut off latent heat effectively. but the sensible heat flux remains large. And that will warm and dry the atmospheric boundary layer and reduce cloud cover. And their study is focused under one specific synoptic condition, so to the east side of the surface high pressure system. And because they use CloudSat and Calypso dataset, so their domain of study is limited south of the 82 North. So in this study, we're going to use the ICESat-2 dataset to examine the overall lead effect in the Pan-Arctic area. So we use the ICESat-2 dataset because it has several advantages, especially for this project. The first of all is it measures the sea ice and the clouds simultaneously. And also these measurements are in really high spatial resolution. And finally, because of the inclination of the ICESat-2's orbit, the pole hole is much smaller compared to CloudSat and Calypso. And this allows us to perform a Pan-Arctic analysis, including the high Arctic north of 82. The data we use is mostly from ICESat-2 datasets. We use ATR-07 for the surface type identification, and we use ATR-09 for cloud masking. The method is really straightforward, so we just collocate the surface data ATR-09 with the cloud data ATR-07 and the cloud data ATR-09 using their timestamps. And to examine the clouds associated with leads, we use ATR-09 profiles both directly over leads and within a certain distance on both sides of the leads. So this is to take into account of the downstream development of the cloud plumes. For clouds associated with sea ice, we only use ATR-09 profiles that are directly over sea ice. To further focus on the clouds that are directly related to leads, we define cloud plumes using the first layer of clouds from the surface with the cloud base lower than a certain threshold values. And then we aggregate all the ATR-09 profiles into 200 kilometer by 200 kilometer grid boxes and compute cloud fraction just using the number of cloudy profiles over the number of total profiles. So here are some results from our study. So this is what I show here are the spatial and seasonal variability of low-level clouds in the Arctic. And we can see that this is from ICESat-2 dataset. And we can see that both the spatial and the seasonal variability is consistent with previous studies using CloudSat and Calypso. And this is basic sanity check for us to proceed. And now we can look at the lead effect on cloud covers. So what I show here are the cloud plume fraction over leads on the top left and cloud plume fraction over sea ice on the top right. And their differences are shown in the bottom left. And I will explain the bottom right plot in a minute. So we can see that there are fewer clouds over leads compared to over sea ice. But does that mean that leads have a dissipating effect on cloud cover? The answer is probably no, because there's another factor here. So synoptic weather conditions is a really strong forcing for both leads and clouds in the Arctic region. And that can lead to erroneous lead effect, which I will explain in the next slide. And before that, let's step back and think about two ways of computing lead effect. The first one is just the difference of the mean of the DOM. So we use the differences between the seasonal mean cloud fraction over lead and the seasonal mean cloud fraction over sea ice, and we use their difference at the lead effect. That is the panel C, the bottom left here. The second method is the mean of the difference. For this method, we consider each granule segment inside the 200 by 200 kilometer square grid boxes, and we compute cloud fraction over sea ice and cloud fraction over leads for each individual granule segments, and we use their differences as the per segment lead effect. Then we aggregate all the per segment lead effect together and to compute the seasonal mean lead effect, and that is what is plotted here in panel D. So we can see that using these two different methods, the computed lead effects are quite different. Using the first one, we got a strong dissipating effect on clouds, and using the second one, we got a much modest dissipating effect. So which one should we trust, and if we can trust anyone at all? So to examine that, I will show the erroneous lead effect by synoptic forcing using an idealized example. So here, let's just consider two ICESat granule segments. Because the length of the granule segment is relatively short, so we can assume there's no subgrid scale variability of cloud fraction, and also because we want to, for simplicity, we have these two granules in the hypothetical world where there is no lead effect. So because there's no subgrid scale variability in cloud fraction, and also because there's no lead effect, the cloud cover over lead and cloud fraction over sea ice, it's the same within a single granule segment. So now we can compute the mean lead effect, mean cloud fraction over lead from these two granule, and we can compute the mean cloud fraction over sea ice from this two granule. And if we compute the lead effect using the first method, we will always find a negative lead effect because the cloud fraction over ice over leads is always smaller than the cloud fraction over ice. So in a world with no actual lead effect, using the first method, we computed erroneous negative lead effect because of the synoptic forcing. But when we use the second method, because the cloud fraction is the same over sea ice and over leads, so the per granule segments lead effect is 0. And when we aggregate the two segments together, the final lead effect is still 0. So using the second method, the computed lead effect is not affected by synoptic forcing. And that is because in a relatively short segment, we can assume the synoptic forcing is similar for both sea ice and leads, and that synoptic forcing is removed in a per segment lead effect calculation. And eventually, the final lead effects will not be affected by the synoptic forcing as well. And this method is possible because of the ICESat can observe the cloud and sea ice simultaneously in really high spatial resolution. So then let's tie this idealized example back to the ICESat observations. We can examine the covariability of leads with cloud. So here we divide the ICESat granule segments in each grid box by their lead fraction percentile. So we have two groups. The first group of segments have fewer leads, and the second group have more leads. What are shown here are the cloud fraction over lead and over sea ice for the first group with fewer leads in the first column, and the cloud fraction over lead and over sea ice for the second group with more leads in the second column. So we can see that when there are fewer leads, there are more clouds, and when there are more leads, there are fewer clouds. So we have a negative covariability of lead and clouds. This is the same as what we have in the idealized example, and because of this negative covariability, computing lead effect using the difference of the mean using the first method will produce a negative lead effect, erroneous lead effect, just as what we have shown in the previous slide here. So now we can conclude that we should use a second method to compute the lead effect, but we can also examine the synoptic forcing that is behind this covariability. So for example, when we examine the mean sea level pressure between the two groups, we can see that when you have more lead fraction, fewer cloud cover happens when there are higher mean surface pressure. So, and finally, here's the conclusion. And using the ICESat-2 observations, we have shown that there is a modest overall dissipating effect of leads on the cloud cover in the Arctic in the wintertime. But this overall effect is much weaker than the results from Lee et al. For a specific synoptic condition. So this much weaker overall dissipating effect suggests that there are competing mechanisms under different synoptic conditions over different type of leads. And that's what we are going to pursue in our future study. And I want to stress again that synoptic forcing is very important for evaluating the lead effect on clouds and has to be removed to produce a correct lead effect. And finally, the ICESat-2 dataset is critical for our analysis, but we also acknowledge there are limitations in the ICESat-2 observations for this study, especially when there are opaque clouds. It obscures the surface detection as well as the low-level cloud identification. And that's all I have. Thank you for your attention.
Thank you so much, Zhenglu. And I think I'm just going to hold off to any questions until we get to the discussion session. So I will ask our next speaker, Renato Ramos da Silva from the Federal University of Santa Catarina, to go ahead and come up. And I see you there. And I will go ahead and share your presentation and give you control in just a second here.
Okay.
Actually, let me see if I can. There you go. And I will mute myself here, but I will assign, and you should see the grant access sign on your side. Okay, Renato.
Okay. Right. Let's see. Thank you very much for the invitation, and I will talk about the applications of the ICESat for the South America region. I am new also using this data, and first I did show some of the results of the workshop on lidar measurements in Latin America last year. There is some publication here as well. I would like to acknowledge my colleagues here that is working with me. Let's see. Okay, we have the dry season in the South America every year at this time of the year, like during the fire season, we have lots of biomass burning. Mainly during September, that is the dry season of the region. And we can see here a satellite image with the fire spots and the smoke. And during this time of the year, occasionally we have cold fronts. We have here in the South Brazil a cold front moving at the same day. And we are concerned about this interaction between the cold fronts and the smoke, because we can have some feedbacks in this region. And at this time of the year, we usually have the winds blowing from the north, east of the Andes. It's a kind of low-level jet that moves and brings all the smoke from north to the south. And eventually it meets with the cold fronts, and we have here in the south cyclone, showing the winds at about 3.2 kilometers height. It's about the height where the smoke is moving. And if you look at this particular biomass burning, when we burn the vegetation and biomass, we emit several components, including gases and particles. The major gases are like the carbon monoxide, nitrogen oxides, CO2, methane, VOCs. But beyond the gases, we also emit primary organic aerosols and black carbon. Black carbon emissions from these fires have the optical property to absorb solar radiation. Their presence can affect the atmospheric thermodynamics, such as the local radiation balance and air temperature. So we look at these locations, and in our study, we estimate the smoke aerosols and clouds height from the atlas, the ICESat tool. We focus in September 2020 when there was a large number of biomass burning fires and smoke aerosols over the Amazon and the South America region. One of the questions we have is to try to understand how smoke aerosols may affect the atmospheric thermodynamics of this region. And so we start looking at this particular region and searching for days with large amounts of smoke. Initially, we look at daily images from the polar orb satellites such as Terra, Aqua, NOAA, and Suomi. We did identify the spatial location of the smoke plumes and clouds over that region. And then we use the ICESat to tracks to analyze the location of the smoke and the height of these features. And in order to do that, we first select our region of interest here in South America, and then we search for the ICESat tracks for that particular region and the September 2020. And then we set three major criteria for the case study. We analyze the presence of smoke for that particular day, but the three criteria was large areas of smoke aerosols, ICESat tracks over South America, that particular time and region, and availability of radiosonde profiles near the observed satellite tracks. So we could have some understanding of the atmospheric thermodynamics. Based on these three criteria, we were able to select a case study. If you look at this particular day, we have the two ICESat-2 tracks. One, the ascendant path here in red, and the descendant path in blue at the same day. And the one in red, it crossed near the region between 8:20 and 9:15 UTC time. That's early morning. And the other one was early evening. That is the blue path. And also, we had 4 stations with radiosones. The number 1, it's located in the south of the Amazon, the Alta Floresta. The number 2, Cuiabá, in the central Brazil. Number 3, also Campo Grande in central Brazil. And the number 4, the radiosonde at Asunción, that is in Paraguay. It was inside the cold front. And based on this data, we took the satellite ICESat, and we can see here from a 3D view from southwest. We have here in the south the location of the high clouds, and we have more on the north the smoke. And if you look at the side view, we have here number 1 is the satellite data, the location of the radiosonde, number 1 in the south of the Amazon. The number 2 is inside the smoke, number 3 as well. Number 4 here in the south, showing this height of the clouds. And we can see the 2 tracks. Obviously, the track that was early in the morning, we had this red one, and we can see, for instance, late in the evening. The other one is a little bit higher, and we compute the height of the top layers. You can see here this height from the ICESat. And we notice that we have a little bit higher on the evening as compared to early morning. They are obviously the same day. It shows that the smoke is under the most of the region. And then we look at the radio sounds for these 4 stations. If you look in the south of the Amazon, we notice the temperature and inversion layer right nearby the region where we select the smoke region. And in the center of Brazil as well, we have this inversion layer here in temperature, and in Campo Grande as well. All these 3 satellite locations, we are inside the smoke. The one in Asunción, we can see that we have a very deep convective cloud, and we could not detect any inversion layer at this particular region. And we compute the height from the ICESat, the top layer of the smoke, and we compare with the top layer of the inversion obtained from the radio sounds, from the measured soundings. And we noticed that we were able to see a very similar location where we noticed the presence of the ICESat cloud layers. Finally, some conclusions we had from this analysis is that some of these tracks did show very high clouds with tops reaching about 12 to 13 kilometers height, when there was mainly the presence of the cold front there in South Brazil, and the smoke that was with height estimated about 3 to 4 kilometers. And these local profiles of temperature show from radio sounds, these show inversion layers at the same detected height of the lidar sensors. These inversion layers seems to be associated with the warming effect of the absorbing biomass burning, mainly the black carbon. So the results show that the lidar onboard the ICESat is an important tool for monitoring this region, as smoke seems to have an influence on the atmospheric thermodynamics on clouds and rainfall formation. This is an important issue because if we have the dry season, we may have some kind of positive feedback because it's dry, you have more fires, you have more smoke, and if the smoke has this stable inversion layer, it can have a drier environment because you don't have the clouds and rainfall formation over that region. So finally, we have like further, which suggests that we may have analysis that could combine other sensors, such as the cloud microphysical parameters that we hear that we may have in the future. These cloud microphysical parameters that would be very important to understand better this interaction between smoke and cold fronts, and probably use ground lidars as well to have some views from the point ground and compare with the lidar from the ICESat. And obviously, if we have these radio sounds on the track of the ICESat, it will be very helpful to understand better the thermodynamics of the atmosphere. Thank you very much. I will be glad to have some collaboration in the future. It's just some preliminary results, But we are glad that we are having this data available. Thank you very much.
Wonderful. Thank you so much, Renata. That was a great presentation. And so this brings us to the part of our agenda where we have our second discussion. And so I am going to invite Melanie Cook to join us here. And so Melanie, as I mentioned at the beginning, is a research scientist in the Mesoscale Atmospheric Processes Laboratory at NASA Goddard. And she's also a project scientist and trainer for the ICESat program. So I have asked Melanie to help us lead the discussion today. I'm going to go ahead and pull some questions that we put together for this discussion, and we will also address some of the questions that you have asked in the chat. So let me just bring that up real quick here. Okay. Okay, great. Melanie, would you like to say a few words perhaps about your impressions so far and lead us into this discussion? Oh, unfortunately, you're breaking up a little bit on my side. Let's try your audio again. No, you're breaking up a little bit. Earbuds. That one sounded a little better. Could we try up a little bit again? Okay. And let me take off. Can you try again? I think I removed there was a CC. No, unfortunately.
Oh, okay.
Oh, there you go. Okay, that's better.
Okay. Can you
Perfect.
hear me
Thank you.
clearly? Can you hear me clearer than before?
Yes, now I can hear you fine. Thank you.
Okay. I can always hop off VPN if it starts to interfere.
No, we can hear you fine now. Thank you, Melanie.
So I just wanted to say thank you for inviting me. I was extremely unfamiliar with ICESat 2 products and particularly atmospheric products. So it's been great to learn about the possibilities and hear the way that it's already been used. And it's particularly relevant for me. I am also involved, I'm on the applications impact team of the Atmosphere Observing System mission. Andrea spoke about that earlier today. And so it's really exciting to hear about all the different ways that ICESat 2 is already being used and could be used in the future in that gap between Calliope and AOS. I know we've heard about a lot of other sensors like EarthCare, Aeolus, but yeah, it's been great to learn about all these potential possibilities.
Perfect.
So I see, would you like to start with discussion or should we start addressing questions? Because I see questions popping up in the chat.
Yeah, let's go ahead and address the questions in the chat. I was just pulling up on my side here.
Okay, so I know at the end of the last break, Dave Jones posted a couple of questions.
Yes. Yeah. So Dave, and actually, I can unmute you here. You were going to tell us about Geo Collaborate. So let me just go ahead and unmute you so you can share a little bit with us about this collaboration here. So let me look. Okay, there you go. Can you hear us okay, Dave? Let's see. Are you here, Dave?
It looks like he's still muted. Well, maybe we can ask his question for him.
Yes.
So first he said, specifically speaking to bathymetry, is it reasonable to assume that ICESat-2 could provide before or after bathymetric, I hope I'm pronouncing that right, measurements of coastal rivers pre and post hurricane or coastal storms? It could potentially be useful to NOAA for emergency response.
And so, Ute, I know you addressed the bathymetry topic. Is there anything else that you would like to say about that?
Yeah, I mean, in essence, what I put in the chat, it's one of the things the bathymetry group is trying.
Yeah.
So I think it'll work. And people have looked at signals in image data and ICESat-2 data.
Perfect.
So there is a bunch of work and publications sort of in progress. Yeah.
What is the typical latency of those types of products?
It's not a product, so we yet have to make an algorithm to find this out and compare to other people's algorithms and so forth. Once this is done, it's presented as a research result. When that is done, perhaps it can become a product. So, but there are people in bathymetry who are working, I mean, they have postdocs and students and so forth. So other than atmosphere, where the algorithms presented here are already products available to the community, there have been from the beginning. The difference with bathymetry is that no one expected ICESat-2 could have a shallow water bathymetry measurement capability, okay? And so that's why there is quite a bit of time lag. It's recognized now, this is a wide area of applications. And so
Yeah.
people are looking at it. It's not like it'll never work, but if you want to pull a ready product off the shelf, you may have to wait.
Yeah, I think there was there was definitely an expectation that it would go down to about 10 meters, but the depth that we're getting from ICESat-2 has been quite remarkable. But going back to atmosphere,
yeah, right.
going to Dave's other comment. I think Dave, are you there now?
Hi, can you hear me okay?
Yes, we can hear you.
Oh, great. Thank you. Sorry, the mute button was giving me a fit. It wouldn't go off mute.
It's all right. Thank you.
Well, yeah, I know that Sabrina, you mentioned GeoCollaborate, and we developed this technology under a NASA Small Business Innovation Research program. And now we have reached phase 3, which means we've spent years refining it and going through all these hoops and gates to get it to a point where it's actually being used operationally in other federal agencies. But what it does is it creates a real-time collaborative environment for anybody sitting anywhere around the world. And everybody is then placed on the same map at the same time, looking at the same data. And it's led by a leader, so a subject matter expert could access data, let's say from ICESat-2 and then maybe MODIS or maybe some NOAA platforms, and bring those data sets together and look at them collaboratively. So it would display on everyone's system, no matter what platform they're using. So everybody's looking at that same data. And then what we found is that it really accelerates the ability to tell a story for how data works together, to access and use federal data together as sort of like one federal family, and also to then do things like CalVal stuff, to calibrate and validate instruments if you have in situ observations like ocean buoys or things like that. So it's that's why I asked Randy about the test bed for FAA. I was like, oh my gosh, we could really get a lot of different NASA products and NOAA products together into FAA to look at just look at different data sets at the same time. Thanks.
Sabrina, you're muted.
Hey, Dave, that's very interesting, and I think very valuable. That what you guys are doing, and it also addresses. There's another question, Sabrina, down the bottom. from Santiago, and he asks, ICESat and space lidars are fantastic when used synergistically with collated observations from other sensors. And, so that's exactly right. I mean, the data by itself, has some uses, but when combined with other things, other data sources, it makes it much more valuable. And Santiago goes on to ask something about worldview, which I'm not real. Yeah, here he goes. But are there any plans to port ICESat quick looks or even level 2 data to portals like Worldview? And, so the Geo Collaborate that you were talking about, Dave, sounds something similar, where you bring a lot of data together and you can work with it in one place. And I think if that could be set up for ICESat 2, I think it would open up a lot more users for ICESat 2.
Yeah, I did want to give the opportunity, Sabrina. I think you were muted when you were talking before, so I do have some ideas I'd love to share after you say
No,
what you
that
were
would
going to
be
say.
great. Yeah, yeah, I kept talking to myself, unfortunately. But I guess I just had a question about sort of that support for emergency management, Dave. Given the discussion that we had on latency earlier on, so what do you think about the latency for ISA 2 and how would that affect the work that you're thinking about?
Well, there are various stages of response and emergency management, and we work very closely with a group called the All Hazards Consortium, which has 45,000 members. They range from state emergency management agencies to DHS, FEMA participates, and then also private sector organizations like the food, fuel, transportation, communication, utility sectors that are I'm on 2-hour calls with them every Friday and have been for the last 7 years. So it's really interesting to see what they need when they're trying to use environmental observation data, satellite information. They want to understand this stuff better so they can put it in their processes for improving their logistical movements across the country, for responding like utilities respond to restore power quicker after a disaster happens. So even though I think I heard ICESat 2 data was 3 days latency, that could be okay depending on what we're trying to communicate and what these groups want to know. But we have a great system set up with the All Hazards Consortium using GeoCollaborate to get on the horn with them anytime and test products and say, how does this look to you guys? What do you think? And many of the responses are that the products have to be easily understood because they make very quick decisions, like 30-second decisions. And they don't want to, they have to know that they trust the data and trust the data source, and that they can, I think what they're trying to use the data to inform their decision-making process. We used to talk about data-driven decision making, but that term is kind of waning a little bit because people don't want the data to make the decision. It's the human in the loop that's making the decision. So it's very interesting, and that's we work a lot with the emergency management side of the house.
Thank you for that. And is that a sort of the Geo Collaborate? Would that be something that, for example, Santiago could access?
Yeah. So the benefit of the Geo Collaborate environment is it's collaborative, right? So if the ICESat 2 group wanted to connect with Santiago and display some products and explain to him what they meant and what they do, and combine it with other products, like whether it's VIIRS on NOAA platforms or MODIS on Aqua and Terra, or other platforms. I mean, I had mentioned when Randy was talking, I wonder for the global precip data if they're using CMORPH for CMORPH2 or GPM, from NASA. The Global Precipitation Mission is really measurements system is really very impactful, and it's updated every hour. So that's the benefit that GeoCollaborate brings. You can put products in front of people, get their feedback, merge it with other things, turn on real-time observations, and it's all based on web services. That's why I asked in the very beginning, are any of these products available via web services, because that's what makes it easily shareable in the web environment, and can pull people together to look at the same data at the same time.
I don't know if anybody else wants to comment, but I think that is wonderful, and I definitely would love to follow up with you on that and see how we can get ICESat in there.
Yeah, no, that'd be great. And the benefit with SBIR, which many people don't know, because many people work on funding SBIR projects, like we're a program manager, project manager for a specific project. But once you get to phase 3, as a small business, you become sole source with every federal agency in the US government. So any agency can immediately start working with GeoCollaborate, to help them better use data. That's what it's all about.
Perfect. Well, thank you for sharing that. I am not able to see, Melanie, the screen because I'm sharing the slide here. Were there any other comments or folks that? Yes.
Well, I think, I see Steve has his hand up, but so Santiago made an additional point, are there any plans to facilitate tools to help scientists beyond something like GeoCollaborate to co-locate lidar observations with other satellite observations? I personally use a worldview hack to view the orbits of, say, Calypso or the ISS for cats, or ICESat-2 to see if a lidar has intersected like an event that I might be interested in. But he's suggesting that ready-made tools might make the lidar data more easy to use with other satellite observations.
Perfect. Yes, and we are going to have a talk by the NSIDC on the tools and services that are currently available. But I know that Mike also shared sort of his how he extracted the data from Worldview. So I don't know, Mike, do you have any insights into that?
I just wanted to comment that the whole thing about tools and data access and stuff, there isn't really much work been done on providing tools for ICESat-2 atmospheric data. And, we kind of looked into that a little while back, and there's some some blockades to that, having to do, gosh, what would you say, Sabrina? Just bureaucratic, NASA generated blockade for putting tools out there. But I wanted to ask this question. We have this question there that says, how easy has it been to access and interpret the data and transform it into usable information? And there isn't a lot of people on the call right now that can answer that, but there was at least 2 or 3 that have used the data. And I kind of would like to know from them, what was their experience like actually taking an ATL09 and making sense of it. Is anybody there can answer that? Maybe no one is willing to answer that.
I can give my experience here in Brazil. First, I found this new data and decided to use it. So I decided to take one of the files, but it was too big. If you take the full track, it's a very big file. So then I decided to have a subset for the South America region, so I could manage that I could download. and we did use Python. So we did open the file and start looking inside what we could explore. And that was not our experience so far.
So you use the subsetting available on, I guess, at NSIDC?
Yeah, that's right.
Right, to just subset your area of interest.
That's right.
And you found that was okay. That worked well.
It did work. It took some time for us to look at all the variables and to see all the possibilities, but
Yeah.
it did work. Yeah.
Right.
because we knew Python. That's right.
Did you also download the user guide?
Yeah, I did. Yeah.
Okay. Okay, because that hopefully, did you find that helped?
Yeah, it did help. Yeah, I was able to read and did learn. And also, before I had some NASA, they have some training, and I did had some training on the ICESat. I don't remember which ones. Probably on. I did use the open altimetry for other data. Perhaps the atmosphere could be in the open altimeter as well. I don't know if it's possible.
Yeah, the open altimetry is, is for the altimetry products, I believe.
We should write to Siri Joda and Adrian Borsa again. I've suggested that before.
Right.
That the ATL 09 or whatever the atmospheric tracks get put onto open altimetry.
Yeah,
that
that
would be a question for Amanda as well.
Pass this on. It shouldn't be that hard for them to do.
Right.
Yes. Well, thank you for that insight. I'm actually, so we have a couple of minutes left in this discussion, but I wanted to bring in Jim Mitchell, who's joining us today from Louisiana, from the Department of Transportation and Development. And I asked him to share with us, how he's using atmospheric data and perhaps some of his thoughts based on what he has learned today from our conversation. So I have just unmuted you. Are you there?
Not getting any feedback.
Was that you?
Yes, this is Jim.
Oh, perfect. Hi, Jim.
Hey.
No feedback whatsoever.
So I'm a recovering academic, so I don't work with a whole lot of data anymore. I'm an IT guy, but I do work and support people in operations. And as you've mostly discussed today, operations guys want stuff for like now or the near future. Yeah, they want the forecast. But there are a lot of things that, like a 3-day window, aren't so bad. I mean, in the emergency response, we do a lot. We're responsible for debris pickup, and we have to deal with ports and waterways and things like that. And so maybe even bathymetry could be something that would be of use to us, but in particular, before and after. So if we know what something was before a storm, and we can get measurements fairly quickly afterwards, then we can figure out whether there's been any significant changes in a channel, for example, or a lake or whatever. The other things are things like, is it going to flood? I'll get a call, on a rainy night with a big storm coming in, and it's like, we need to know how high the road is on this highway because we think the river might flood, those kind of things. So, those are like more immediate needs. But I do think that, one man's data is another man's model. And really, mostly what we work with are models. And I would say in the emergency management business, emergency management people are not very hands-on data oriented. They want to see the process data. They don't have the time or knowledge, for that matter, to process it. The people I work nobody uses this data. We might use a product from it, but we're not using the data. So, that has to be delivered to us in a fashion that we can use it as information.
Yeah, thank you so much for that point. There's always this aim to accelerate applications, but getting from those raw data to the actual useful information and making it in a format that works for you, and that could be readily accessible. That's a very, it's a different conversation as well, right? So there's many steps along the way to getting to an operation.
Well, and I think as an IT guy, it's got to come to us over the web as a web service.
Okay.
So we can grab it and not have to download a bunch of files and transform them in this form and that form and, analyze them on our end, right? Picture's worth 1,000 words.
Wow. Great. Well, thank you so much, Jim, for sharing those insights. Melanie, did we have any other questions, or?
Well, I saw
you'd like to
Shane
ask?
Liu had their hand up as in response to Steve's question about how easily the data was downloaded and used. I didn't know if you wanted to unmute and say anything.
Oh yeah, I'm still here. So I just have a comment because for getting familiar with the data and using the data, NASA has been hosting this ICESat Hack Weeks for many years, and that is a good starting point to learn the tools and to get familiar with the data. And for the ATL9 data itself, and Jessica will talk about that probably later in the afternoon, that using SPICs, you can actually subset the variables as well, not only the domain and the variables. For ATL9, one largest one is probably the backscattering profiles. And if you don't really need that, you only need cloud mask, you can just download the other variables. That can significantly reduce your data size. And yeah, that's much easier to manage, I think.
Well, that's good to know that IcePix has some tools there already that could be used for the atmospheric data. So thanks for saying that.
It is in Python, so
Yeah.
it's for people familiar with Python, it's probably easier. But I think in the package there are also example notebooks that should be easy to follow. And yeah, again, going to the Hack Weeks will be really helpful.
Perfect. And so Jessica will be talking to us about IcePix in just a couple of minutes. We do have a break, and we're into our break. I do have a burning question for Randy about blowing snow. We've talked with Ute and with Steve about perhaps doing hazard warnings for blowing snow. And I wonder, in aviation, is that something, how does that affect aviation? Is that something that you're looking for in this type of data, realizing that perhaps the latency won't work here?
Generally, not really. Mostly because blowing snow is an airport problem, not a national aviation system problem.
Okay.
So in that respect, it would be more of a local problem. That being said, if it's a multiple airport problem, it's something that we could potentially take a look at. But it's not something that's really come up before, so it would realistically it would be low on our priority list.
Okay. Wow, great. Thanks for that insight. Okay. So we are at 3:20. Thank you so much, Melanie, for helping me facilitate this discussion. We are set to be back at 3:30. Are folks okay with a 10-minute break, or should we aim for a 15-minute break?
Hey, Sabrina, I did have one other comment on that, though.
Okay, please go ahead.
With the influx of UAS activity, that could be something that that they would be interested in on a local level, but it would have to be, a really at that time issue. So again, the latency would probably be an issue there.
An issue there. Okay. Yeah, but it could be a good conversation to have and see if there is some, could be used some other way.
Oh, certainly, because we're not, the FAA doesn't provide forecasts for operations necessarily, only to our controllers. But certainly for the UAS operators, who are going to be getting a lot of their information from third-party commercial weather providers, yes, certainly that could be another input for them.
Thank you, Randy, and I will definitely follow up with you on that. See if you can connect us to the UAS. Okay, so let's come back at 1:30 and we will have our training session. So we're going to learn all about the graded products and iSpecs and the tools available from the NSIDC. So that would be in 10 minutes. Thank you all. All right. Welcome back, everyone. So as I mentioned, the next session is going to be our training session. And so before I ask Tom to join us for his presentation, I will call Bill Sjoberg, who wasn't able to join us in the previous discussion, or I didn't see his email come in time, but he wanted to share with us about what he does at NOAA and perhaps some insights into what he's gotten from the discussion so far. So let me see if I see you here, Bill, so that I can unmute you. Let's see. And I think he might have had to step out. Are you there, Bill? Okay. I will just have to follow up with Bill later. Okay. So thanks for your patience there, Thomas. So our next speaker is Tom Northam. He's Chief Engineer, Chief Computer Scientist at the Department of Atmospheric Sciences at NASA Goddard, and he's going to tell us all about the graded product for ICESat 2.
Well, not exactly.
Okay.
Because Steve precedes me.
That's right. Yes.
Yeah, I had my hand up there. I was just wondering whether you still wanted me to do the website.
Let's do it. Yes, on the quick look products. That would be wonderful.
Okay. All right. So this is going to be a live demonstration. Bring my camera up. There you go. Yeah, a live demonstration. I'm going to try to bring up the website and show you guys about the Atmosphere Quick Look website. So let me share my screen. Okay.
And I can see your screen. Yep.
And bring up, there's the website. Some of you may be familiar with this, some not, but I wanted to show everybody that this is a really good tool for, if you had something, some event, in the last 4 years since ICESat 2 has been operating, this is a good way to see if, we have some data near the event or when the event happened. And so you can, set the date up here and then click on the day, the actual day that you are interested in. Right now we're looking at September of 22, September 15th of 2022. And the website is set up to have these different regions where I think I have 12 regions now. And you can see them listed here. And right now we're set up here to look at South America. And, what it shows you all of the passes that go through that box, in this case, South America, for that particular day. And we have the backscatter image shown, as well as the DDA layer detected heights, the top of the layer is shown as yellow dots superimposed on the image, and the bottoms as this reddish orange color. So, you just scroll down. You can click on an image to make it somewhat bigger. If you click on it, it gets bigger. I think if you right click on it, you can save the image, to your local machine. And so, once you bring up a date, okay, whatever the date is, you can scroll through the various regions and, you know, it'll bring up that region very quickly, as you can see here. But when you change the date, okay, let's go to, I don't know, what's a good date? Halloween? October 31st. It's kind of scary. But what it does is the system the web server brings up all the images of all these different regions. And so it takes a little while for them to load. And you see them just listed here by their names. And once the whole loading process is done, then you'll see the image pop up. And then once that loading process is done, then you can easily scroll, you know, from one region to the next. So it's taking a little bit of time here. It usually doesn't take this long, but it is taking, oh, there it goes. There it goes. Okay. So all the images have populated for that particular date, which is October 31st. And we could scroll through, you know, the various regions, and they would come up immediately. Wow, that right there is the best example of folding I have ever seen. This cloud down here really belongs up there. That's amazing. So anyway, that's the website, and the URL is there somewhere here in the box. Where is it? Right here. ICESat 2 and Atmo data. So that's a good tool for you guys to use when you want to look at if you have data near an event that interests you. Okay, Sabrina, that's it.
All right, great. Thank you, Steve. And I just shared that link in the chat for folks as well.
Okay.
So
good.
Tom, please take it away. And Steve, I think you have to stop sharing there. Yeah.
Yeah.
Hey, Sabrina, this is Mike Fromm. Can you hear me?
Yes.
I don't mean to insert myself here, but since Steve just showed that, I wanted to ask two questions. One is, does this work on all browsers? It seems my default browser is Firefox, and it seems to me either those images don't load up at all, or they load up very slowly. Whereas if I paste that URL into Chrome, it actually is faster and more predictable.
Interesting, Mike. I do not know. I use Firefox as well. So that demo we just did was Firefox.
Okay.
And I have not tried it at Chrome, but maybe it will be faster, like you say. So that's something I'll look into.
Maybe I just didn't wait long enough, but I thought I had waited a while and wondered if it was just that. So anyway, I'll play with it some more, but I appreciate knowing that it does work there. The second question is actually having to do with folding. Since you brought that up, I didn't mean to ask earlier and now ask again. When those folded data are shown, are they actually added to legitimate data at those altitudes? So it's like a combination of what you would get without the folding and the folding, or does it replace what would be there without the folding?
Yeah, it's the former, Mike. It actually is an additive process. The scattering that exists, let's say at 2 kilometers above the ground, would be added to the scattering at 17 kilometers above the ground.
Okay.
And shown at the 2 kilometer height. And so that's why, you know, if you have a thick opaque cloud that's up at 17 kilometers and is realized at 2 kilometers, well, you know that that's the only scattering there because it's opaque. But when you have, let's say, you know, some of your anvil blow off cirrus up at 17, that's transmissive. That is folded down to 2 kilometers and added to whatever's there. So it's sometimes hard to interpret, you know, what it actually is.
Okay, well, I appreciate that info. Thank you.
Yeah.
Thank you, Mike. Okay, I think everything's working on your side, Tom.
Okay. Well, greetings in this afternoon, everyone. I'm Tom Northam. I'm with SSAI, and I work out of Wallops Flight Facility, Wallops Island, Virginia. And my job, hopefully here briefly this afternoon, will be to do an overview of the ICESat-2 atmosphere gridded Level 3B data products. And for those of you who are familiar, we'll be sharing some new information. For those who are not, this will be hopefully an introduction. There are two Level 3B atmosphere gridded science data products. The first is the ATL-16, which is a weekly product. The second is an ATL-17, which is a monthly product. Now, you would think for a weekly product that there would be 52 products per year. We're working off of the Julian calendar, Gregorian calendar, where months are probably our temporal range. And so the monthly files will contain 28, 29, 30, or 31 days, of course, depending on if we're in a leap year. The weeks will always appear in monthly boundaries. Now, this means there'll be 4 weeks per month. The first 3 weeks of every month will be 7 days in length, starting with the 1st, the 8th, and the 15th. The last week of each month, depending on February or February leap year, will be 7 days or 8 days or 9 days or 10 days for the 31-day month. And I just mentioned that because if you haven't looked at that data, you might not recognize that. But that's how the data gets divided. I'm privileged to work with Steve Palm, a lot of experience as our lead scientist in atmospheres and in meteorology. Okay. And I'm having a page down problem. Page up, page down.
Are you able to click on the presentation?
Well, I can now, but, okay. I lost my pointer, so I'll just have to use the mouse. I just want to mention here that we work with an atmosphere team. Steve is our lead. Dr. Yokwe Yang from Goddard is part of our team. His area of expertise, he helped provide the radiation ancillary data that we use. Professor Dr. Uta Hersfeld from University of Colorado Boulder is responsible for the famous density dimension algorithm for atmospheres, which is so vital in the processing that builds the ATL-9. David Hancock out of Wallops is our ground system manager. Our developer for the level 2A and the level 3A atmospheric products is Christine Barbieri from Greenbelt. Adam Hayes is a graduate research assistant at the University of Colorado Boulder. Where does our data come from? And this is all important. We are so dependent on the ATL-9 level 3A. Solely, this data product provides all of the input that gets gridded. Now, this product is known as the Atlas ICESat level 3A calibrated backscatter profiles and atmospheric layer characteristics data product. It's 1 orbit per file. There are 10 data groups and subgroups within each file. We primarily work out of the Profile X high rate group. This is 25 hertz data, 25 per second, and there are approximately just under 141,500 points, retrievals, shots per profile. We also do take some data from the 1 hertz, the low rate profiles, and this is approximately just under 5,700 points, shots. We call these retrievals per profile. Each ATL9 contains 3 profiles, and these are the rendering of the 3 altimeter strong beams, the left, center, and right. The data I'm displaying today is from the ICESat, the Atlas Science Algorithm Software Functional Test Data Set, known as 960B1. This is version 5 data, which is currently available, or if not yet, will soon be. I'm using a set of 556 ATL9 HDF products, quite a bit of data. These are clusters of cycles and reference ground tracks that cover from October 14th of 2018 through August 15th of 2020. The exhibits I'll primarily be using today will be the monthly products produced from this data set. Normal 28-day month will have 428 ATL9 data in it for the month of February, non-leap year. For a 31-day month, there are 474 ATL9 files for a month such as December. By note, the 556 ATL9s we're using here makes for a fat or a saturated ATL9. This is really the mathematics of the process. There are 2 phases for every gridded parameter algorithm. First is the collection. And depending on if we're weekly or monthly, if we're global or polar, the array sizes change. But in the top is a numerator collection grid, and in the bottom is a denominator collection grid. And so as we process through the profile data based on criteria, selected profile shots, observations, retrievals get loaded into the numerator array either as a sum of counts or as a sum of the actual retrieved profile values. The denominator is generally the running sum of all the available retrievals, shots, observations in that particular array. In the cases of frequency or in the cases of when we do an average gridded product, this denominator will be somewhat lessened. It will be a selective set of retrievals. After all the ATL9s, all the profile data for the particular control set has been processed, we go into the computation phase. And in the computation phase, we are actually dividing the numerator array by the grid array in the denominator, and we're getting either a fractional value, a frequency value, frequency may also be in percent, or we're getting an average value. This is kind of a simple way of looking at the algorithms. The numerator array, generally for fraction, contains the filtered count, the filtered retrievals. The denominator contains all of the available observations, and this renders a fractional value generally between 0 and 1. Frequency is also a 0 to 1 value. We again are filtering the retrievals in the numerator array to whatever algorithm we're working with. And in the bottom, we tend to have in the denominator a filtered array of observations based on some criteria. In the case of we want frequency and percentage, as we do with blowing snow, we multiply the 0 to 1 value from frequency by 100 to get a range of percent from 0 to 100%. The other form that we retrieve in the gridded product is the average. And in this case, the numerator gets the values of the acceptable retrievals as a running sum. The denominator array gets a running sum of the observation counts. And when that division occurs, we're getting an average value. I'm showing here an exhibit of the global image in a rectangular projection. It happens to be global cloud fraction. The range of the global data is always 360 degrees in longitude by 180 degrees in latitude. The origin of the data in this happens to be, first of all, the South Pole, minus 90 degrees, 90 south, and minus 180 degrees in longitude or 180 west. The ATL-17 discriminates from the ATL-16 in the size of the collection cell and the amount of data that goes into it. And in the particular image I have here on the top right, I'm showing you that the ATL-17 grid size is 1 degree by 1 degree, while the ATL-16 grid size is 3 degrees by 3 degrees, and that makes for the product cell size for the 16 being 9 times the area of what it is in the ATL-17. Of course, in the 16, we're collecting 7 to 10 days. The spots in the box are just representative of the numerator and denominator shots that are going into the cell. Certainly, we will be putting much more because we're processing 28, 29, 30, or 31 days of data. When all the data has been assimilated, we do the computation, and that leaves us with a single representative value per cell, which I'm showing in the bottom as a color-coded value. And that is the fractional value, the frequency value, frequency in percent, or the average value. We change size when we go to the polar. Now, I mentioned that the global has an origin of the South Pole and minus 180 in longitude. The North Pole comes from a different aspect. Here, we actually have an origin of the North Pole plus 90 degrees and minus 180 degrees in longitude. And again, I'm showing the sizes of the grid here. The ATL-17 has a size of 1.5 degrees in longitude and 0.5 degrees in latitude. Comparatively, the weekly product has a 3-degree longitude by 1 degree latitude grid, and so the area in the ATL-16 cell is 4 times that of the ATL-17. Again, more data in the 17 with 28, 29, 30, or 31 days, with the 16 containing either 7, 8, 9, or 10 days. I just show the South Polar. The grid size is the same as it is for the North Polar. The origin is the same here as it was for the global, and that is our 0 point is the South Pole and minus 180 degrees in longitude. First product I want to share with you is our global apparent surface reflectance. What I'm showing here, and this is for a reference for all of the products, when you get this plate set after Sabrina posted on ICESat, the first thing we show is this is the gridded parameter that goes on the product. We also include the count of observations or retrievals that goes into the denominator grid. The image of the projection is actually embedded in the data product. We are collecting as well statistical values, which we also call quality assessment values. We're grabbing the min, the max, the mean, the standard deviation. Now, I want to just touch briefly on the key data that goes into this particular parameter. And this is the apparent surface reflectance. The apparent surface reflectivity represents the true surface reflectivity modified by the two-way atmospheric transmission. As we've said, it's generally between 0 and 1. The ASR is related to the ratio of the received energy to the transmitted energy, assuming a Lambertian surface reference. And so in this particular case, we have to have a value for our primary profile element where the signal is greater than 0, indicating that we do have a surface reflectance. Now you'll notice at the top it says modified. Historically, this parameter has been in our data set from the first version at NSIDC version 2, version 3. Currently, version 4 is out there. Version 5 is the new version we'll be delivering. But The modification is now that we're constraining the data going into this product. And the data is constrained primarily by a computation using the profile beam elevation. We compute a laser off nadir angle from the beam elevation, and we are constraining the data here to a laser off nadir angle limit of 6 degrees. We collect the same data for the North Polar region, 90 north to 60 north, 30 degrees in latitude. We do the same process for the South Polar apparent surface reflectance. Again, this is 90 south to 60 south, 30 degrees in latitude. A product that goes back to our first delivery to NSIDC is the global column optical depth. And here the data that goes into this is the optical depth from the apparent surface reflectance. This is the optical depth of the atmosphere column based on the apparent surface reflectance and the assumed actual surface reflectance. Now, why is this modified? In the previous versions of this parameter, 2, 3, and 4, we have constrained this data to using the quality flag for the retrieval, and we were reporting only over water data. With the version 5 delivery now, this will be opened up to include valid retrievals over land, sea ice, land ice, and water. And so this is opened up. Now, there are constraints placed on this data. We are now constraining the column optical depth ASR to a value range greater than 0 and less than 4. And again, we're applying the laser off nadir angle here that we have to have less than 6 degrees for the laser pointing off nadir. New parameter coming up in this product is the global cloud fraction from the apparent surface reflectivity. And here we're using the ASR cloud probability. This is the probability of the occurrence of clouds based on the magnitude of the apparent surface reflectivity. Now, we set a threshold on this data that we have to have a value of 70% or greater in order to count clouds in the numerator. And then, of course, the denominator here is all the available clouds. We collect this same data, this same algorithm for the North Polar region, 90 north to 60 north. And again, the same is done for the South Polar region for 90 south to 60 south. We now move into the global cloud fractions, and now we're into the realm of the dimension density algorithm for atmospheres. And so our data here comes from two sources in the ATL9 data. The first is the cloud flag ATM, which gives us a count of the number of layers determined by the DDA. This can be up to 9 layers. There is also an array in the profile that goes along with that, which gives us the layer attributes for the layers that the DDA has retrieved. And the values are no layer, cloud, aerosol, or unknown. In this particular case, in order to have clouds, we must have at least one cloud layer of type 1, which is cloud. That's the criteria we use to load the numerator, all available observation retrievals going in the denominator. A cousin to the global cloud fraction is the combined global cloud fraction. And here in this case, we're augmenting the clouds retrieved from the DDA layer finding algorithm with the ASR probability. So in the case of where we don't have any layer retrieved by the DDA, or the layers retrieved by the DDA do not have a cloud type, then in that particular cell, that for that particular shot, that retrieval, we substitute the ASR cloud probability count again for ASR cloud probabilities exceeding 70%. So again, here the DDA clouds count is augmented in the absence of a count value with a count from the ASR cloud frag. Here we're again presenting that data in a global image only. This also comes from the DDA algorithm, the global aerosol fraction, and in this case, we're using the number of layers and the layer flags. And in this case, from the up to 10 DDA determined layers, we have to have one layer of type 2 as an aerosol. And if that's the case, we count into the numerator and the denominator being all available observations. Also, from the DDA layer finding, we determine the global clear fraction. And in this particular case, we're looking for no layers retrieved by DDA, which means we have obscuration, or we have an inability of the DDA to determine clouds. If we do have clouds determined, all of the layers up to 10 have to be aerosol type, indicating we have a clear sky column. Now, we also collect cloud fraction in the polar regions, north and south polar. And I'm showing here by example, again, the north polar region, 90 north to 60 north. And in this particular case, in the up to 10 cloud layers from DDA, we have to report at least one layer of type 1. Same for the south polar region. We have to have at least one cloud from the up to 10 layers in the region of 90 south to 60 south. Now, I want to mention just in passing, I'm not showing them here, they're in the supplementary area. We also use the layer top parameter from the profile data, and we determine cloud layers, and we also report this data as low clouds, which are surface to 4 kilometers, as middle clouds, which goes from above 4 to including 8 kilometers, and then high clouds with a layer top that is above 8 kilometers up to the bin limit for the retrieval, which is around 14 kilometers. We also collect data along with the surface signal using the cloud flag and the layer attributes from the DDA. We are now testing the surface signal, which is the surface return bin. It's the count of the number of photons in the detected surface bin. And so we have to have signal. And if we have a signal value that is greater than 0 and at least one cloud layer, we count this as a transmissive cloud in the north polar region. And again, we're dealing with 90 north to 60 north. We do the same thing in the south polar region, 90 south to 60 south. Now, we've talked about the transmissive sky. Now we're dealing with the opaque cloud fraction. And in this case, we have a condition of where we look in our layers. We have to have in our up to 10 layers at least one cloud flag value of 1 indicating clouds, and the surface signal has to be 0, indicating there was no return in the detected surface bin. This same algorithm is applied in the south polar region, 90 south to 60 south. And now we move into polar precipitation. This is the blowing snow frequency for the north polar region, 90 north to 60 north. In this particular case, we're using 2 parameters from the profile data. We're loading the numerator in a count form with data that comes from the blowing snow height. The blowing snow height is the layer thickness in meters. It is also the height of the top of the layer above the surface. And so if we have blowing snow, we count that in the numerator. The denominator is loaded from the blowing snow confidence flag. And in this case, we have to have a confidence level of at least -2 or greater in order to consider the occurrence of clouds. And that is how we get our cloud fraction. And this gets reported in percent. We collect the same data for the South Polar region. Again, here, this is high rate blowing snow. And the reason I'm indicating at high rate here is because we're at the point of using the 25 hertz, 25 per second high rate data. We also report out the low frequency, the low rate blowing snow, and the low rate blowing snow for the South Polar region as well. That goes back to our first version, and we still continue to report those out. And Sabrina, I'm getting a note that I've exhausted my time. I can yield if that's a reasonable point to do so.
I can give you 4 extra minutes.
Okay. Well,
Thanks,
here's the new kid on the block. This is South Polar surface diamond dust. And in this particular case, we're using the diamond dust height bottom for the density layer. We're converting that from the ellipsoid model down to the surface. We want to make sure we have a diamond dust layer that reaches the surface, that we have a surface return in the surface bin, and we're not in the presence of blowing snow. And then we count that in our numerator array, and the denominator array gets any value with any retrieval with the surface bin value. This is our final parameter. This again goes back historically to versions 2, 3, and 4, ground detection frequency. And here again, we're employing the surface signal count, the number of photons, and the detected surface bin as our trigger for counting this particular data. And in this case, we have to have a surface return in order to say that we have detected the ground. And so the numerator gets loaded with the detections, the denominator gets loaded with the available retrievals, and that gives us a fractional value from 0 to 1. We also collect that data in the North Polar region, 90 north to 60 north. And again, for the South Polar region, 90 south to 60 south. I want to mention for a moment here that the expectation is that ATL 16 version 5 and ATL 17 version 5 are expected to deliver sometime in January 2023. And if we have another minute left, Sabrina, everybody's been talking about latency. I can add a few comments about that just for information if you'd like that. If not, we can hold it till later.
We have 2 minutes, and we have a question from Lauren about do you have diamond dust for the Arctic as well?
Well, we are not reporting that now, but I believe, Steve, if you're available, the door is open that sometime we will probably add to the product the North Polar region diamond dust.
Yes, we could do that easily. The reason we do it over Antarctica is because it's, well, somewhat more prevalent, and it's also, as you know, Antarctica is a desert. And there are places in Antarctica where they get 80% of their precipitation from diamond dust, or also known as clear air precipitation. So that's where we first started, but we could easily expand that to the Arctic to include Santa's workshop.
And thank you, Steve and Tom. So I think I'm going to go ahead and switch to Jessica now. But if Tom, if you would like to maybe put some of those comments on the latency in the chat for us, I think that would be great.
Okay.
But appreciate the presentation. That was great. And so, yeah, just in the interest of time, I think I'll just move to Jessica's presentation on ICEPICS. And Jessica is from the University of New Hampshire Earth Systems Research Center. So thank you so much, Jessica.
Thanks, Sabrina. When you start sharing your screen, they move all the controls on you.
Oh, yes, that happens. Thank you.
Let's see. There we go. So, hi everybody. As Sabrina said, I'm at the University of New Hampshire Systems Research Center. I also do have an affiliation with the University of Washington's eScience Institute, where I work on their Hack Week team. And what I'm here to talk to you about today is something called IcePix, which is both a community as well as a piece of software that is for working with ICESat data. So I want to start by really emphasizing this community aspect. You can see here just some of the people who have contributed to the code that is in the software library. Some of the faces pictured there are people who are in the room today. And then, as I said, IcePix is also a software library. One of the things that makes us really strong and as a community is the fact that this group includes not just researchers, which is the perspective that I come to working with ICESat data from. I have a background in glaciology and remote sensing, but it also includes developers, data managers, and data users like you guys on the applied teams. IcePix came to be at an event in 2019, something called Hack Week, which was organized by the ICESat science team to really help researchers who were funded on the ICESat mission to do science and really help them get up to speed on what are the data sets that are in ICESat, what are the products, what do they look like. So all of these ATL ... whatever numbers, what are those products, what do they look like, and how do we work with them? And the idea, and one of the things that came about at this meeting was several of us noticed that a lot of the folks in the room were all sort of spending time recreating some of the same basic tools to work with these new data sets. And we said, okay, can we collaborate on this and really bring people together and create a space where we can all put the code that we're using and modifying in a central location so that people can really get from that initial data discovery and access step to their science and applications much faster. And as you can see from this chart that we like to use to describe ourselves, community is really at the base of that. And teaching some of the basic skills that are needed for us to all effectively collaborate on working with these data sets together. For those of us in academia, many of us are not taught these skills as part of our academic training. And so we're trying to really create a collaborative space where people can experiment with some of these new tools. And so with that, I just want to say, what does it mean to really be a part of this community? We really emphasize being cooperative and working together. We're not necessarily in a rush, which can be really important when you're learning a new skill. We do a lot of peer-to-peer learning, which is a really great way to help solidify new skills that you've learned. And everything that we do is completely open and everybody is welcome. So moving more formally to the IcePix package itself, as a piece of software, what is IcePix and what does it do? What does it have? So some of the things that you might be used to seeing in any software package are IcePix has a full documentation page. It's easy to install. If you're familiar with Python and working with Python libraries, you can install it via the Python package managers Conda and the Python package index. IcePix includes examples of all of the different functionality. For some data sets, namely those that are available through the Open Altimetry platform, we have some interactive visualizations. And most importantly, the reason that IcePix came to be is that it really tries to minimize the amount of code that a user needs to implement in order to access and read in their data and really get to the part where they're doing fun science and applications. And so with that, some of the things that are really critical for working specifically with this ICESat-2 data is that we're able to, IcePix includes functionality to read in data. And as you've seen from some of the other presentations, this data comes in granules. For the atmospheric products, they're often a single granule covers the entire world, but maybe you're not interested in looking at the atmosphere globally. Or in the case of a lot of other products, those products are coming as granules that cover a much smaller spatial extent. And so in order to study a specific region, you might need to stitch together multiple granules. And so IcePix has capabilities to read that data into one big data set without you having to manually open each of those granule files and paste them all together. The other thing that IcePix has that's really, I think is really awesome for working with ICESat-2 data is, as you saw in Steve's presentation earlier today, there are a lot of variables that are included in these data products, but very often we're only interested in a few of them. And IcePix has its own variable management system that is aware of how these variable groups are structured in these HDF5 files. And I would like to give a shout out to Zhang, who you also saw present earlier, who is a driving force behind making this variables module a reality. And so what it allows you to do is to pick and choose which data you actually want to read in, rather than having to manually create a list of all of these different groups and paths to your variables. You can automatically populate that list and then say, here are my files, here's that list, and I want you to read it in for me. And so with that, I'm actually going to transition to an example. So can somebody confirm that you can see this Jupyter notebook?
Yes, we can see it.
Cool. Great. Okay, so I'm going to move forward with talking about this workflow. And I'll say this workflow I put together over the course of the past week. And with some help from Steve on what pieces of ATL09 to target, and also thinking about a specific area to look at. And so this notebook is publicly available. I can put the link in the chat. It's also available in the presentation. And as I said, it's a very new workflow. So it will not yet appear on the IcePix documentation site. It's only on our GitHub site, but it will eventually go through the process and get itself there. So for those of you who might or might not be familiar with Jupyter notebooks, they're a really great way for showcasing Python code because they allow you to have both plain text and code all at once. I'm going to more or less skip through a lot of the text that is in this file because it is explanatory and meant to help guide you through the workflow in the absence of myself or someone else explaining it to you. So just to start with, when we start using any new software package, we have to go ahead and import it. I also want to note that I am not actively running this notebook as I'm giving the presentation, just so that we don't have to wait for any of the compute steps. And also because I've been having trouble connecting to the NSIDC via the web as of a couple hours ago. And so luckily I had some data downloaded already that we can work with. But so as I mentioned before, when we start working in a region, we're often looking for a particular period of time, a particular spatial region, or something of the sort, just to get ourselves started. And so here we're going to look specifically at the northwest coast of Africa. There are multiple different ways to define a spatial extent that you put into IcePix. But one of the most common is to use a bounding box of latitudes and longitudes. We know that the short name of the product we want here is ATL09 because we're working with the atmospheric product. And then we're going to look specifically at this date range because Steve told me ahead of time that there were some cool features to look at for those days. So once we have this information defined, we can go ahead and create what's called a query object within IcePix. And this query object holds all of this information, and it will make sure that it's formatted in a way that can access the data directly from NSIDC. We want to make sure that everything's working well. We want to see where this area is. We can use this visualize spatial extent function when it's really zoomed in. It's obviously hard to see the whole map, but this is an interactive map. You can pan around, maybe. There we go. So we can see here that we're working in this region off the northwest coast of Africa. So before we go ahead and order and download our data from NSIDC, we might want to know how much data we might be getting. And so we can look at what the number of granules that are available and, roughly how big they are if we download all of them. We can also look by adding this IDs equals true flag and see what the actual file IDs are. And so, for example, we can see these three here. The next step that we're going to do is just to log into NASA's Earth Data System, which I know Amanda will talk a little bit more about in the next presentation. This is just how you get authenticated on NASA's website. Anybody can sign up for an Earth Data login. It's completely free and open. It just helps them track data downloads. And so we're going to go ahead and log in. And then we are going to go ahead and order and download our data. We'll have to specify where on our system, whether that's a local system or a system in the cloud, we would like to have that data downloaded to. And then we go ahead and download that data. This sometimes takes a few minutes. IcePix will keep posting updates for you, so you know that something's happening. You'll see here this data request is submitting to NSIDC, and eventually it'll go through and say, okay, we're waiting for the orders to process. Okay, all of your orders are ready. We're downloading your files. Your files have been downloaded. As I said earlier, I was having some connection issues, and so we actually have an error message here instead of a nice printout of what was happening. But fortunately, I downloaded some data ahead of time, and so we're still able to go through with the reading in of that data. So to read in the data with IcePix, we have to first define what is called a pattern, a file name pattern. And this is because certain information that is contained in the file name of an ICESat-2 data product is not contained in the file itself. And it makes it easier for us to then later sort of parse out the data and keep track of the file if we can just tell IcePix this is what the file name format looks like. But this is really flexible and you can define this however your file names are formatted. So it's completely customizable. From there, we're going to say, okay, we're going to create this what's called a reader object. And what this does is this is reading in the data. This is going to give IcePix all the information that it needs. So in this case, we're letting it know where our data is located. We're letting it know that we're looking for ATL09 data. And we're letting it know what that file name pattern is. You'll see we only have one file matching this pattern, and that's rather than the 3 granules that we saw returned by our search before, and that's because of I only had one pre-downloaded. And so returning back the next step that we need to do is we need to tell IcePix which variables we actually want to read in. Which ones do we actually need to have in memory relative to what's in the file? And so here we can get a list of what variables are available in a given file by taking a peek at the first file in our list. So you can see here, we've got quite a long list of variables. And so for our purposes, what we want to do, see, I'm still in A. Here we have our profile, we have the high rate, and then we'll get to the low rate, and then eventually we'll get through the other profiles. So you can see it's a very long list. So which variables are we actually interested in? I'm interested in anything that has this cab prof field, so the calibrated backscatter, latitude and longitude. So what I do is I append and say, these are the variables that I'm actually interested in. And then I can say, okay, just to make sure we're on the same page, IcePix, which variables are you going to give me? You can see there's a few more here than the ones in this list, because there are a few that IcePix needs behind the scenes to keep track of that data and combine it properly. And there's also a few defaults that are always included for everyone, such as the date. But what you can see is that rather than having to create a list for each of the profiles, say, manually create a list that says, I want, profile 2 high rate latitude and profile 3 high rate latitude, you can see that whichever is available in this data set is now included, all of the latitudes, regardless of which profile they are and which rate they are. Alternatively, we could request only things that are high rate or only things that are profile 1. So this variables module allows you to have that flexibility to really hone in on the exact data that you're interested in. From there, we simply say load the data, and it gives us what's called a data frame. For those of you who are familiar with Xarray, which is an awesome package, and it allows you to have labeled indices for all of your data. And so what you can see here is that we have our granule index. We have one granule. We can see here in this parameter, we can see the name of the source file for that granule. We have an index for each of the photons. We have, this is called spot. I'm in the process of updating this to read profile for the ATL09 data sets. But this is our profiles. We have 3 profiles in this particular granule that we've read in. Here's our vertical height bins. And then this photon index is because Xarray requires a unique identifier for every single piece of information that's in there. And in some of the data sets, the delta time is not unique, and the photon ID is also not unique. So it just creates this unique photon index to keep track of that data. And then we can see here all of the variables that we've read in, including this calibrated backscatter. And what this is showing you here is this calibrated backscatter depends, there's calibrated backscatter values that depend on which profile it is, so that spot, which granule it comes from, the photons, and then also there are different calibrated backscatter per height. So knowing this about our data, we can go ahead, and what I've done here is I've just selected one profile. So I've just selected that first profile. And now we have a slightly smaller data set that we're working with. And then the thing, few small things for working with Xarray data that we need to do in order to plot it. For instance, it does not handle nans, so we have to fill the nan values. And then we can go ahead and use this functionality to create our plot. And so we can see here this plot of the Saharan dust for this day in June of 2020. And the thing I'd like to draw your attention to is that it's a little hard toggling back and forth, but we can generally see that the character of this plot is very similar to the one produced by that quick look image. But I've done this locally all on my machine. And so this allows you to really have an interactive way that you can zoom in on certain pieces of the data set and customize them yourself once you've seen those quick look products and use them to identify the pieces of data that are most useful for you. And so with that, I will return to my slides and make a few plugs for what is happening now with IcePix and where we're going. So I didn't really mention this throughout the presentation, but IcePix actually enables both traditional data access via download from NSIDC, or by changing a flag in one line of your code, you can also transition to accessing that data in the AWS, the Amazon Web Services S3 bucket that hosts the data. That data is only fairly recently available. So some of these tools are still in development. But if you run into any issues, if you are trying to work in the cloud, I'd love to hear about them. We're improving some of our authentication mechanisms, adding more data processing. IcePix is participating with something called CryoCloud, which I think is relevant to some of the things that folks were talking about in some of the discussions earlier, thinking about how collaborative computational environments and how we really bring our data sets together, but also bring our computing together. And so CryoCloud is an effort within the cryosphere community to start experimenting with some of that type of shared infrastructure to work collaboratively in the cloud on these data sets rather than having to pull things local and work on them locally. Another effort I really want to highlight is the Quest component of IcePix. So Quest is an acronym that stands for Query, Unify, Explore, Spatiotemporal. And this is a group that actually started at the 2020 ICESat 2 Hack Week. And what they are doing is they are creating a templated way to bring in and combine multiple data sets with ICESat 2 data. So we're usually looking in a specific spatial or temporal region. And so rather than needing to redefine that information for every data set, we're sort of flipping that model on its head and saying, okay, well, we already know the time and space, and now we'd like to be able to bring in this other data set. How do we manipulate that information to bring in this other data? And so this effort is really focused right now on using on Argo float data. But the idea is that it's creating this template that will make it easier to introduce some of these other sensors. And so if there's one you're interested in using or adding, we would love to work with you on that. And so with that, here are some resources. Happy to share any of these links. Feel free to get in touch with me, and thanks for your attention.
Great. Thank you so much, Jessica. That was wonderful. And I think, you stressed it a lot, and it's, that it's a community as well. So, you can always put your code in there and share what you've done. So this is a great way to do it. And you have Jessica's contact here for any questions on IcePix. So thank you so much, Jessica. And we do have Dave Jones, who says, have the ISEP Federation, or the Earth Science Information Partners Federation, would be very interested in welcoming you to their winter meeting. Have you participated in any ISEP meetings?
I did once a while ago with Pangeo.
There you go. So you have an invitation for the winter.
Thank you.
And thank you, Tom, as well for putting the information on the latency in there for us. Okay. Are there any other questions for Jessica before we move to Amanda? Steve, yes.
Hey, Jessica, thanks a whole lot for that that presentation. That was awesome. I didn't really know that you were going to get it all the way through to actually seeing Saharan dust. So it was good.
I didn't either, but
yeah, yeah, I think it would be really great if I could learn this stuff. So is there like a user guide? Is that part of your documentation that, can help someone like me, a dinosaur, actually actually learn this stuff?
Yeah, yeah, definitely. And I would also encourage anyone who's interested in learning about some of these things in more detail to check out the ICESat2 Hack Week materials. There are videos and tutorials that you can work through as well. So you get a much broader perspective on some of these various tools as well. And
Okay.
catch you up on
Yeah.
any basics you're not familiar with.
And the other question is, I think you mentioned somewhere in your presentation that you can, you took that ATL09 for a specific area. Now, suppose I wanted to add ATL03 for that particular area at that same time. Is that, doable with this, that you can bring that in as well?
Yeah, so for so I don't know if you remember the step where we said we're going to read in the data. We actually
Yep.
specified which data product we wanted to read in. You can only
Right.
read in one data product to a given object because of the way the data products are structured. But that being
Right.
said, Xarray, the tool that we're reading it into, the way that it works with those labeled indices, we could have we could basically have a little bin of ATL09 data and another little bin of ATL03 data at the same time. And then we could use the tools that are in Xarray and say, we want to combine these things, or we want to compare these things. And because you have those labeled indices, it can do things like match by date or match by latitude to start combining those data sets
Okay.
the way you'd like
And
to.
then one last question was, the actual display of the data there, you saw the image of the Saharan dust. Was that something you had to code in Python, or was that just something, like one call to some routine? How did you do that?
The figure I produced.
Yeah, the final image.
So I mean, it was a few lines of code in that I had to supply a couple of different parameters. Like for instance, you had provided me with like focus on these levels of the atmosphere, sorts of things. I used the quick look calibration backscatter scale bar as a way to focus on, what portion of the data I would really want to look at. So that's why it's a few lines, is because you're defining some of those different parameters for the software. But the figure itself, yeah, I mean, I didn't count them, but I would guess that we could probably make the whole notebook work in maybe 20 lines of code.
Cool. All right, that's really cool. Thanks a whole lot, Jessica.
All right. Yes, thank you both. And I did try to share the link for the Hack Week that was hosted back in 2022 or this year. And just an announcement that there will be another Hack Week next year. So stay tuned for that information. Okay. So thank you, Amanda, for joining us. And so Amanda Leon from the National Snow and Ice Data Center, Distributed Active Archive Center. She is the manager of the DAC at the NSIDC. So thank you, Amanda. And Amanda, we're not hearing you.
All right, better?
Yes, thank you.
Thanks. Hi, good afternoon, everyone. Yeah, I'm Amanda Leone. I am the DAC manager at NSIDC, where ICESat2 data are stewarded and distributed. Also very active in ICESat2 work here is Lisa Kasser, who is our data management lead, and Michaela Beige, who has been on the call a lot today. She's often at the hackathons. And Walt Meyer, I didn't list here, is our DAC scientist who's been involved in ICESat2 as well. So Jessica just did a really great look at a particular service that's available for use with ICESat2 data and for the community. I'm going to come up a level a bit and share some of the services and support that the DAC has for ICESat 2.
And Amanda, we're seeing you're not in full mode, if you want to do the full mode.
I'm going to try not to. My machine kind of freaks out. So I will zoom in as much as I can, but sorry.
No, and we can zoom in on our side. Thank you so much.
Okay, thanks. Yeah, so I'll cover the services and tools we offer, and not just software tools and services, but briefly talk about the support, the science support and the data support that we do offer at the DAC. And I will try to demo the website very briefly. We're coming up on the 5 o'clock hour. So what I'm going to talk about is available for all of the atmospheric products that are produced by the mission and available at NSIDC. So there are the 3 standard level 3 products as well as the quick look products that have been more recently released. So there's a lot of capabilities that are available for all of these data products. So starting with more of the support and data resources that we offer, if we have an ICESat 2 collection site, which is really our knowledge hub for everything about ICESat 2 and the mission. On this page, you can get access to all of the ATBDs and other mission documents. There's also help articles for ICESat 2. So from this point, you would get access to all of the ICESat 2 articles. There are a page that tracks the published papers citing ICESat 2. So if you're interested in applications of ICESat 2 data on atmospheric conditions or something like that, you can come to this page and see maybe what published research is already out there. And then from all of our web pages, we have a support button. And this goes to real humans. Our fantastic data and user support team will receive an email if you fill out this support form, and will help you with data access, data selection questions. So there's a lot of information available for ICESat 2 from this page. And I didn't go through all of them, but you see there's other things like announcements and data tools. So from the collection site, you can also go to the data page and eventually end up at an individual data product landing page. And like the collection site being the hub for the mission, this is the hub of information and access to tools and data for an individual data product. So I won't go through everything available on these pages, but I will note that there's quick links to some very commonly needed information, like the data product user guide. So this is the comprehensive description of the data structure, the algorithms. It has references to the ATBD, but it really tries to summarize the key information about the data products, its derivation, and how it's structured in the files. There's also a quick access to the data citation so that you can cite data and give credit to all of these data authors who are producing these products. And then if you're interested in getting updates about a particular product, there's a subscribe button so you can get on our mailing list. And whenever we are publishing a new version, or if there's some change or something to be aware of in the product, we will send out a notice. So on this page, data access and tools is something that you can get to, and that's what I'll spend the rest of my time talking about. So for each product, we will surface exactly which tools and services work for that product. And there's also a lot of help articles specific to this product or more broadly that you can access from here. So I will click through these pages in a minute live so you can see it again. But stepping into the tools and the services that we have available for ICESat 2, one of the important capabilities that we are providing is the ability to customize ICESat 2 data. So there's the native HDF file and the number of variables that are in that file, and that file might cover a particular spatial area. We have customization services which allow you to subset that file to your spatial, temporal, or parameters of interest, variables, parameters of interest. So if you're not needing every variable in the file, you can extract just the ones that you're interested in. And then we also enable you to reformat the data to something other than HDF. So ASCII, GeoTIFF, and NetCDF4 are available for all of the atmospheric products, if that's the format that works with your workflow better. And this service is being utilized by tools like IcePix that are calling our API to access and obtain data in maybe a subsetted format. So we try to draw the distinction that this is different than when you go into a map interface and you draw a box and you pick your region of interest. Like, this is actually changing the data file that you'll get to subset it down. And with ICESat-2, volume can be larger, so this can be beneficial to reduce the size of the file that you're working with, or remove all those variables that you're not interested in. So we do have a number of tools and services, and that's because there are many different types of data users who have different workflows. And so we're trying to support a broad community of different application and use. So I'm categorizing what we're offering in kind of two dimensions. One is it a graphical interface? Is it a GUI? Or is it a programmatic access, a script-based, API-based access? And then some of our tools and services do that customization that I mentioned, but others don't. So if you're just trying to get your hands on the files in the native format, you don't need to reformat them to NetCDF or GeoTIFF. There are some things that let you do that, including our now direct S3 AWS access. So that was, we recently distributed all or released all ICESat-2 data in Earth Data AWS, Amazon Web Service, a couple months ago. So this just kind of maps out the different ones. And you'll see in the middle here, I have Jupyter notebooks. So these are, I'm showing them in the middle because they do kind of blend that user interface with programmatic. And we know that these are a very popular and useful way to get started with ICESat-2 data and to engage with community members who are doing the same. So the IcePix notebook, we have the ICESat-2 hackathon notebooks, as well as our own NSIDC data access notebook. So each of these tools or services, we have access to them, but we also have tutorials to help you learn how to use them. So this is a list of some of our common, more core tools and services. This is, I'll show you in a minute, they're on the dataset landing page. It's a little card that shows you the tool and service, and we have them tagged with these keywords to help you more quickly determine, is this one going to be useful for what I'm trying to do? Am I trying to visualize? Am I trying to customize? Do I just want to get data? We do know there's quite a few, so we're trying to help users determine which tool or service is best for their application. But for each of these little tool and service cards, there's also a link to a guide that helps you learn how to use them. And I also wanted to call out, we recently did an Earth Data webinar where we walked through our website and the different ways to discover data. And there is a live demo of our data access Jupyter notebook available in that webinar that starts at 35 minutes after, if you want to see a demo of the notebook as well. Okay, so let me jump over to the website and just kind of reflow through some of these options. So there's a number of ways to to discover and access ICESat-2 data on our website. We come at it from a number of different approaches, whether you're thinking about a particular mission or a type of measurement. So one way is to come in to explore data, and then we have ways to filter down by collection method, geographic area, measurement. So if you know you're looking for ICESat-2, might come in this way. And this is how one way that you can end up on that ICESat-2 collection page that I mentioned. So here's the ICESat-2 hub with documentation, help articles. We have all the ATBDs. And a very important page is the data page. So here is the list of all available data products. And there is occasionally multiple versions of products available as the mission is going through a reprocessing event. So you can filter down to just the most recent version if that's what we generally recommend that you use the most recent. So this helps you get to it. So if I were to come down to the ATL09 Quick Look product and click on this link, this is how you end up at one of the data product landing pages that have access to everything that you might want to find for this product. And I will note, Jessica mentioned she couldn't access our site. On Wednesdays, when we have our routine maintenance. So banners about if we're going to be having maintenance are available on these product pages to help users understand what's going on with our system. We also put any other kind of banner here about the product in particular. So here's the ones that I talked through earlier. This is one long page of information that gives you a summary of the products, the coverage, and then if you keep scrolling or use these little navigation links, you can end up at the data access tools. So these are the cards that I mentioned earlier. One of the GUI interface tools that we have is the data access tool. And it starts off as an interface where you can temporally and spatially and keyword search for data, and then either place an order through the GUI here, or you can get a download script in Python to directly ingest it, bring in your files. And I'll note that IcePix is maybe not on this one, but we do have a card for IcePix, community developed tools that are really useful for ICESat-2. We curate that information here as well. So it's not just tools and services that the DAC has developed. We also try to link out to things of relevance for the community. So here's the card for IcePix. We also have access to the Hackathon Jupyter Notebook tutorials. So I know, let's see. So I'll just come back to the slides and say there's a number of community engagements that we're actively participating in. One of them is NASA OpenScapes. It's an activity to really train DACs as well as scientists of how to move workflows into the cloud and do it in a collaborative, community supported environment. So we've been very active in OpenScapes, participating in a number of tutorials, and through OpenScapes, a lot of great resources are being developed for scientists interested in moving their science workflows to the cloud. We're also involved in NASA's new Transform to Open Science TOPS program, which is trying to really invest in the infrastructure and the training needed to make science more open and transparent and inclusive. So all DACs are actively engaging in this TOPS program because the DACs will play a really important role in helping to further promote open science through open data and open software. There is an opportunity for, don't have my top expert on the call, but there is an opportunity called the Champions Program through OpenScapes, where science groups, research projects can sign up to be a champion and engage in the OpenScapes program and really work to move a particular science workflow into the cloud. But we'll be doing some webinars going forward on cloud and NSIDC DAC services. So there's lots of different ways that there's training going on across the community. So yeah, there's a lot that is available. Sometimes it can be hard to find or know what is there. And so you're always welcome to reach out to NSIDC. We are here to help navigate the tools, the data, that, how to visualize, access, subset, anything that you might want to do with the data, we can support you in that usage. And so this is our email address that you could reach out and someone can support you with that. Thank you. Any questions? I'll stop sharing here.
Thank you, Amanda. I don't see any questions on the chat right now, but are there any questions for Amanda at this point? And we can, if you can raise your hand. I did share the link to the demo that you had in the slides.
Thank you. Yeah.
So folks,
yeah, and I put a number of links in my slides just as reference for after the meeting. Those are shared. There's links to all the different pages I showed and some resource links.
Yeah, so thank you so much, Amanda. And I should note that we are recording this this whole focus session, and so I know we did have issues with the registration and people coming in, and so we will share this publicly. So I will be sending out the link to that recording, and of course we welcome you to revisit all of the information and to share it with colleagues and spread all of this great information that was shared today. I know I've taken a lot of takeaway points and ways to follow up with folks here on the different things that were mentioned. I also mentioned that we were going to put together a report to synthesize all of the feedback and ideas that we have shared so far. So in this last few minutes, I just wanted to invite both Steve and Ute to give us some final words today. But on my behalf, I want to thank everybody for being here, for the time that you've taken to put together all of this great talks and for all of the feedback that we've received from attendees. So thank you. And with that, I'll hand it over to Ute and to Steve to close our meeting.
Hey, so
Go ahead.
First,
Go
thanks
ahead,
to
Ute.
Sabrina. Do you want to say the final word, Steve?
Yeah, whatever. You go first, Ute.
So then you have the final word. Okay, anyways, I guess we both agree we should say thanks Sabrina for a glitch-free operated workshop here. It was really interesting. We learned a lot of new things actually from the other missions, from all the users, and definitely there's no shortage of help available for users to access the data, at least as far as I can see. And yeah, of course, people are invited to further say what's needed if they see this otherwise, and we hope the user community will just grow and grow.
Yeah, very well said, Uta. And I want to also thank Sabrina for doing an excellent job in hosting this and putting this together. I really appreciate that. I only wish that we had done this maybe a year or two ago. But I think it really has helped, people understand what the ICESat-2 atmospheric data products are, how to use them. We saw 3 or 4 other users showing us how they're utilizing the data. And the presentation by I believe it was Jason on Calypso, was excellent to see all the different applications that Calypso data can facilitate. And I'm hoping that some of them ICESat 2 will be able to be used for as well. I love the IcePix presentation. That was awesome, as well as NSIDC, seeing various tools that we can use. And I really hope to be able to use those two tools and how to use them. So thank you again, Sabrina, and everybody who participated. I think it was very, very useful.
Wonderful. Thank you all. And I do want to acknowledge sort of the comment that we have from Dave Jones. As NASA looks to engage additional users for their data, it will be necessary to simplify the way in which data is accessed, understood, and used. Thanks for having this workshop. So I think I will leave it with those final words. And you have all of the contact information. I will be sending out the list of all that participated today. So feel free to reach out to Steve, to everybody with your questions. And with that, thank you and have a great rest of the week.
Thanks, Sabrina.
Okay. Thank you, Sabrina.
Bye.
Thanks. Take care. See you soon.